Something just skipped past Mars without flinching, and now it's racing toward a region of space we've barely mapped. 3I Atlas, the third confirmed interstellar visitor, has completed a planetary flyby that should have bent its trajectory, yet orbital calculations show almost no deflection. While NASA's billion-dollar spacecraft captured blurred images and mission teams celebrated coordinated observations, amateur astronomers revealed something the official gallery left out. This object is moving with a precision that makes gravitational models uncomfortable. The trajectory isn't just unusual, it's heading toward a zone where our understanding of orbital mechanics breaks down. What happens when an interstellar visitor ignores the rules we've built our planetary defense systems on? The data is already forcing us to rewrite the playbook. The Mars flyby that shouldn't have been clean. Mars and 3I Atlas cross paths in a celestial near miss that orbital dynamics predicted would leave measurable consequences. Standard gravitational calculations expected the comet's trajectory to bend by several arc seconds as it passed within the Martian sphere of influence. The Mars Reconnaissance Orbiter, positioned to capture the interaction, recorded the object at a distance of approximately 19 million miles on its closest approach. High-resolution tracking data from multiple observatories coordinated their measurements to build a precise orbital solution before and after the encounter. The preliminary results revealed an anomaly that mission planners hadn't anticipated. Post-flyby trajectory analysis showed deviation values significantly smaller than gravitational models predicted. JPL's orbital determination team ran the calculations repeatedly, adjusting for solar radiation pressure, outgassing forces, and potential mass distribution asymmetries. Each iteration produced the same uncomfortable result. The deflection was minimal, bordering on negligible. For an object estimated between 1 and 5 kilometers across, passing that close to Mars should have produced a clear gravitational signature in its path. The Mars Reconnaissance Orbiter's HiRISE camera attempted to resolve the nucleus during the flyby, but the technical limitations of imaging from nearly 19 million miles away compressed the entire core into a single, unresolved pixel. The team extracted an upper size limit of approximately 3.5 miles for the nucleus, but the actual dimensions remained buried beneath the overwhelming brightness of the surrounding coma. Without a resolved image, mass estimates relied on assumptions about density and composition, assumptions that gravitational deflection data was now calling into question. Radar observations from Goldstone Deep Space Communications Complex attempted to measure the object's mass through echo delay and Doppler shift. The returns were weak, barely above noise levels, but the preliminary analysis suggested a density profile that didn't match typical cometary values. Solar system comets typically show densities between 0.5 and 1 grams per cubic centimeter, reflecting their composition of ice and dust loosely packed together. The Goldstone data hinted at values either significantly lower or distributed in ways that concentrated mass away from the geometric center. Gravitational deflection serves as a direct probe of an object's mass. When 3I Atlas passed Mars without showing the expected trajectory change, it posed a fundamental problem. Either the object's mass was substantially lower than size estimates suggested, or something else was affecting its motion. Lower mass would imply a structure more porous than any known comet, potentially approaching the density of aerogel. Alternative explanations involved non-gravitational forces outgassing jets, radiation pressure effects, or electromagnetic interactions with the solar wind, but none of these mechanisms typically produce the kind of precise, predictable motion observed in 3I Atlas's trajectory. The tracking data from the Deep Space Network painted a picture of an object moving with remarkable consistency. Astrometric measurements precise to fractions of an arc-second showed 3I, Atlas, maintaining its course with minimal scatter. For comparison, Comet Borisov displayed erratic motion as asymmetric outgassing, created random accelerations requiring constant updates to trajectory predictions. 3I, Atlas, exhibited none of this chaos. Its position matched predictions with an accuracy that made orbital mechanics teams uncomfortable, because natural comets aren't supposed to move this predictably. Mission planners at NASA's Planetary Defense Coordination Office took particular interest in the Mars flyby results. Their mandate involves tracking potentially hazardous objects and predicting future encounters with Earth. The gravitational deflection anomaly introduced uncertainty into long-term trajectory forecasts. If the object's response to gravitational fields didn't match standard models, then predicting its future path became significantly more difficult. The office requested additional observation time from multiple facilities to refine the mass estimate and understand the deflection discrepancy. The European Space Agency's Space Situational Awareness Programme independently analysed the flyby data and reached similar conclusions. Their orbital propagation models, which incorporate perturbations from all major solar system bodies, couldn't reconcile the observed trajectory with standard gravitational physics unless they introduced free parameters, adjustable factors that essentially admitted the models didn't fully capture the object's behavior. These parameters had no clear physical interpretation, serving merely as mathematical corrections to force the calculations into agreement with observations. The scientific community's response split along predictable lines. Conservative researchers emphasized the uncertainties in mass determination and argued that better data would eventually resolve the discrepancy. Others pointed out that the Mars flyby represented a controlled experiment, a natural test of gravitational deflection under known conditions, and the results challenged fundamental assumptions. A smaller group began exploring exotic explanations. Ultra-low density structures, internal mass distributions that violated spherical symmetry, or even electromagnetic effects that somehow produced forces mimicking gravitational interactions. As 3I, Atlas continued its journey outbound from the Sun, the Mars encounter became a critical calibration point. The object was now heading toward regions of space where tracking becomes progressively more difficult, where the angles and distances make precise measurements nearly impossible. Whatever the Mars flyby revealed about this visitor's true nature might be the clearest data we'd obtain. The deflection anomaly wasn't just an observational curiosity, it was a warning that our models for predicting interstellar object trajectories contained gaps that could prove critical if another visitor arrived on a more threatening path. The trajectory models that keep breaking. Orbital mechanics operates on principles established over centuries, refined through observations of countless objects moving through the solar system. When 3I, Atlas, first appeared in detection systems, analysts applied these proven methods to calculate its path. Initial trajectory solutions placed it on a hyperbolic orbit with an excess velocity of approximately 23 kilometers per second, fast enough to confirm its interstellar origin, but not unprecedented. The orbital elements seemed straightforward. Inclination near 180 degrees, placing it in a nearly perfect retrograde orbit, and an eccentricity well above 1, confirming it would never return. Standard trajectory propagation involves integrating equations of motion that account for gravitational attractions from the Sun, planets, and major asteroids, plus non-gravitational perturbations from solar radiation pressure and comet outgassing. Software packages like JPL's Horizon system and ESA's GODOT have successfully predicted orbits for thousands of objects with high precision. When these same tools processed 3I Atlas tracking data, the residuals differences between predicted and observed positions showed patterns that shouldn't exist. Orbital determination teams measure an object's position multiple times, then fit a trajectory that best explains all observations while minimizing errors. For typical comets, residuals scatter randomly around the best fit solution, reflecting measurement, noise, and minor unmodeled effects. 3I Atlas produced residuals with systematic trends, suggesting the models were missing something fundamental. Early trajectory solutions required frequent updates as new observations arrived, not because of measurement errors, but because the object's actual motion consistently diverged from predictions in the same direction. The Southwest Research Institute's Orbital Dynamics Group attempted to model the non-gravitational accelerations that might explain the discrepancies. Comets experience forces from outgassing jets of sublimating ice that act like tiny rockets, pushing the nucleus in directions that depend on where the active regions are located and how the object is spinning. The team built detailed thermal models of 3I Atlas's surface, calculating how sunlight would heat different regions and drive gas production. Their models predicted acceleration vectors that should have matched the observed trajectory deviations. The predictions failed. The direction of the observed accelerations didn't align with where the thermal models placed the most active outgassing regions. Moreover, the magnitude of the forces seemed too large for the estimated gas production rates. Spectroscopic measurements showed relatively modest outgassing compared to typical comets at similar distances from the Sun. Yet the trajectory showed accelerations consistent with much more vigorous activity. Either the spectroscopy was missing most of the gas, or the accelerations weren't coming from outgassing. Radiation pressure, the push that sunlight exerts on objects, becomes significant for small particles and low-mass bodies. Calculations for 3I Atlas showed that radiation pressure should contribute to the trajectory, but the effect depends critically on the object's mass and cross-sectional area. Without a resolved image showing the nucleus size, analysts had to estimate these parameters. Every reasonable estimate produced radiation pressure forces too small to explain the observed trajectory anomalies. Making radiation pressure large enough required assuming the object was either extremely low mass or had an unusually large area conditions that didn't match other observations. The trajectory modelling teams faced a persistent problem. No single physical mechanism could account for all the observed motion. Gravitational attractions from the Sun and planets were well understood and precisely calculated. Adding standard outgassing effects improved the fit slightly, but left large residuals. Including radiation pressure helped in some orbital phases, but made predictions worse in others. The models needed multiple free parameters, adjustable numbers, with no clear physical meaning to match observations. This approach violated the principle of Occam's razor, where simpler explanations with fewer assumptions are preferred. By mid-2025, 3 independent groups had published orbital solutions for 3I Atlas, each using different modelling approaches and datasets. All 3 reached the same frustrating conclusion. The object's motion required forces beyond standard gravitational and radiation effects, and these additional forces showed structure and persistence that didn't match random outgassing. The Minor Planet Center, responsible for cataloguing solar system objects, appended a note to their 3I Atlas entry, acknowledging the trajectory uncertainties and recommending that users treat long-term predictions with caution. The planetary defense community watched these modeling struggles with growing concern. Their mission involves identifying potentially hazardous asteroids and comets, calculating impact probabilities, and developing mitigation strategies. All of this depends on accurately predicting where objects will be years or decades in the future. If interstellar visitors like 3I, Atlas, moved in ways that current models couldn't predict, then the entire framework for assessing impact risk needed revision. A fast-moving interstellar object on an Earth-crossing trajectory might not give enough warning time if trajectory predictions carried large uncertainties. Attempts to improve the models focused on collecting more data. Observatories worldwide increased their observation cadence, capturing 3I, Atlas's position, every few days instead of weekly. The denser dataset should have reduced uncertainties and revealed the nature of the non-gravitational forces. Instead, it highlighted how persistent and structured the anomalous accelerations were. The object wasn't behaving randomly, it was following a path that required forces acting in coordinated ways, maintaining direction and magnitude over extended periods. This coordination implied either a very stable outgassing pattern or something else entirely. Some researchers proposed that 3I Atlas might be tumbling in an unusual way that created stable jet orientations despite the rotation. Complex rotation states, where an object spins around multiple axes simultaneously, can produce counterintuitive motion. However, the measured 16.16-hour rotation period suggested simple rotation around a single axis, not the complex tumbling needed to explain the trajectory anomalies. Attempts to fit the data with precessing rotation axes or wobbling spins introduced even more free parameters without improving the match to observations. What MAVEN's hydrogen cloud really means. MAVEN's ultraviolet spectrograph captured data that fundamentally changed the conversation about 3I, Atlas's composition and activity. The instrument, designed to study Mars's upper atmosphere, detected Lyman alpha emission from neutral hydrogen surrounding the interstellar visitor. This emission results from sunlight exciting hydrogen atoms, causing them to fluoresce at a specific ultraviolet wavelength. By measuring the intensity and spatial distribution of this glow, the MAVEN team mapped a hydrogen envelope extending nearly 33,000 miles from the nucleus, a structure far larger than the visible coma captured in optical images. Hydrogen production from comets typically originates from water-ice sublimation. When water molecules escape the nucleus and enter sunlight, ultraviolet photons break them apart through photodissociation, creating hydrogen and hydroxyl radicals. The MAVEN team's initial assumption followed this standard picture. The massive hydrogen cloud indicated vigorous water outgassing. They calculated production rates based on the observed brightness, estimating how much water would need to sublime to generate the detected hydrogen signal. The numbers suggested outgassing levels comparable to moderately active comets in the inner solar system. This conclusion immediately collided with spectroscopic data from ground-based telescopes and the James Webb Space Telescope. Multiple observing campaigns searched for water emission lines in 3I. Atlas's spectrum, the characteristic fingerprints that water molecules leave when excited by sunlight. The searches came up nearly empty. Water vapor accounted for roughly 4% of the gas in the coma, based on the relative strengths of different emission lines. For comparison, typical comets show water dominating the gas composition, often exceeding 80%. The discrepancy was stark. MAVEN detected a hydrogen cloud implying substantial water production, while direct spectroscopy found barely any water. The MAVEN science team revisited their analysis, looking for alternative hydrogen sources. Carbon-bearing molecules can produce hydrogen through photodissociation, though less efficiently than water. Organic compounds like methane, formaldehyde, and methanol all contain hydrogen and could contribute to the observed cloud. However, the spectroscopic observations placed limits on these molecules as well. The detected abundances of carbon monoxide, carbon dioxide, and simple organics weren't nearly high enough to explain the hydrogen production rates MAVEN measured. Something didn't add up in the mass budget. Photoionization complicated the picture further. When ultraviolet photons strike hydrogen atoms with sufficient energy, they strip away electrons, converting neutral hydrogen into ionized hydrogen protons with no accompanying electron. The MAVEN instrument only detected neutral hydrogen, meaning the total hydrogen population included both the neutral atoms it observed and ionized material it couldn't see directly. Solar-wind interactions accelerated this ionization process, with charged particles from the Sun colliding with neutral hydrogen atoms and stealing their electrons through charge exchange reactions. The Laboratory for Atmospheric and Space Physics ran detailed models of the ionization environment around 3.1 Atlas. They incorporated solar ultraviolet flux measurements from the Solar Dynamics Observatory, solar wind density and velocity data from the ACE spacecraft, and chemical reaction rates measured in laboratory experiments. The models calculated how quickly neutral hydrogen would be ionized at different distances from the nucleus, allowing the team to estimate the total hydrogen production rate needed to maintain the observed neutral cloud. The results suggested that MAVEN was seeing only a fraction of the total hydrogen population to the ionized component potentially contained several times more material. This realization intensified the water problem. If the true hydrogen production rate was several times higher than the neutral hydrogen alone suggested, then even more water would be needed as a source. Yet the spectroscopy remained clear. Water was scarce in 3I, Atlas's coma. The contradiction forced consideration of non-standard scenarios. Perhaps the hydrogen wasn't coming from molecules at all, but was being released directly from the nucleus as atomic or molecular hydrogen gas. Some icy materials can trap molecular hydrogen during formation, releasing it when warmed. However, this mechanism requires formation in extremely cold environments, temperatures near absolute zero, and even then, the storage efficiency is low. Another possibility involved subsurface chemistry. Radiation processing of ices over long timescales in interstellar space can create complex organic molecules and alter the chemical makeup of the surface layers. When these processed ices heat up near the Sun, they might release hydrogen-rich gases that don't match typical cometary composition. Laboratory experiments simulating irradiation of interstellar ice analogues showed production of exotic molecules, but whether these products could generate the observed hydrogen cloud remained an open question requiring detailed chemical modelling. The hydrogen envelope's size and structure provided additional clues about the underlying physics. MAVEN spatial maps showed the cloud wasn't spherically symmetric, but stretched preferentially in the anti-sunward direction, shaped by solar wind pressure and radiation forces. The asymmetry allowed calculation of the timescales for hydrogen transport from the nucleus to the edge of the envelope. At typical expansion velocities for gas leaving a comet, hydrogen atoms would take several hours to reach the outer extent of the observed cloud. This transit time set constraints on production rates and loss processes, adding another piece to the complex puzzle of 3I, Atlas's gas budget. Solar activity introduced temporal variability into the hydrogen cloud. When the Sun released coronal mass ejections or high-speed solar wind streams, the increased particle flux enhanced ionization rates, temporarily reducing the neutral hydrogen population MAVEN could detect. The instrument recorded these fluctuations, showing the cloud brightening and dimming in response to space weather changes. This responsiveness demonstrated that the hydrogen cloud was actively maintained by ongoing outgassing, not a static feature left over from earlier activity. The object was continuously producing hydrogen-bearing gases, even as the detection of parent molecules remained frustratingly elusive. The hydrogen cloud data forced a reassessment of what comet-like behavior actually meant for interstellar visitors. If 3I, Atlas, was producing massive amounts of hydrogen without corresponding water detection, it implied either a composition radically different from solar system comets or processes we hadn't encountered before. Both possibilities challenged the simple narrative that interstellar objects would behave like familiar cometary bodies just arriving from farther away. The MAVEN observations revealed an object whose gas production didn't follow the standard comet playbook, adding to the growing list of anomalies that resisted conventional explanation. The coronal mass ejection that missed its mark. Solar observatories detected the coronal mass ejection as it erupted from the Sun's surface, a massive burst of magnetized plasma accelerating outward into the solar system. The Solar and Heliospheric Observatory tracked the CME's expansion, measuring its velocity at approximately 1,000 kilometers per second, fast enough to traverse the distance to 3I, Atlas's position, in a matter of days. Heliophysics teams calculated the arrival time with precision, predicting the leading edge of the plasma cloud would reach the comet's vicinity around October 22nd. Multiple spacecraft, including MAVEN at Mars and the Punch satellites monitoring the inner solar system, prepared to observe what should have been a dramatic interaction. Coronal mass ejections represent some of the Sun's most powerful outbursts, carrying billions of tons of plasma and enormous magnetic field structures into space. When a CME encounters a comet, the compressed magnetic fields and enhanced particle flux can produce spectacular effects. The most dramatic outcome is a tail disconnection event, where the comet's plasma tail material, already ionized and flowing away from the nucleus, is literally severed by the shock front of the incoming CME. This disconnection happens because the magnetic field embedded in the CME has opposite polarity to the field in the plasma tail, causing magnetic reconnection that breaks the tail free and sweeps it away. Tail disconnection events have been observed in numerous solar system comets, with some of the most famous examples captured by amateur astronomers. Comet Encke experienced a disconnection in 2007, photographed by observers worldwide as the tail broke free and a new one began forming. The physics is well understood. The CME's magnetic field interacts with the ionized gas in the tail, the fields reconnect, and the tail structure downstream of the reconnection point loses its connection to the nucleus. The process typically completes within hours, creating a visible gap where the tail was severed. As October 22nd approached, plasma physicists anticipated observing this phenomenon in 3I, Atlas. The comet's plasma tail, though less prominent than its dust tail, was visible in ultraviolet observations and should have been vulnerable to CME interaction. MAVEN's instruments were programmed to monitor the hydrogen cloud's behavior, looking for sudden compressions or brightening as the CME shock front passed through. Ground-based observatories scheduled intensive monitoring campaigns, imaging the comet repeatedly to capture the expected tail disconnection in progress. The CME arrived on schedule, its leading edge crossing 3I, Atlas's orbital position, at the predicted time. Solar wind monitors on spacecraft throughout the inner solar system registered the passage of the shock front, recording sudden jumps in plasma density, velocity, and magnetic field strength, the characteristic signatures of a CME impact. Based on these measurements, the comet was directly in the path of the disturbance. Observation teams waited for the tail to respond. Nothing happened. MAVEN's ultraviolet spectrograph showed no sudden changes in the hydrogen cloud's brightness or extent. The Lyman alpha emission continued at levels consistent with pre-CME observations, without the spike that enhanced ionization should have produced. Ground-based imaging revealed the plasma tail maintaining its structure, showing no sign of disconnection or disruption. Time series photometry, which should have captured the tail's brightness fluctuating as the CME passed through, showed only the gradual variations associated with the comet's normal rotation. The lack of response puzzled the observation teams. They reviewed their predictions, checking whether the CME's trajectory might have missed the comet despite the solar wind monitor data. Detailed modelling of the CME's expansion suggested that its width should have encompassed 3I, Atlas's position, with high confidence. The solar wind conditions at multiple spacecraft matched predictions, confirming the CME was behaving as expected everywhere except at the comet itself. Alternative explanations focused on the possibility that the plasma tail was somehow more robust than typical, able to withstand the CME impact without disconnecting. Magnetic field measurements from solar wind monitors showed the CME carried strong southward-pointing magnetic fields, precisely the configuration most likely to cause reconnection with a northward-pointing tail field. The geometry appeared ideal for triggering a disconnection event, yet observations showed the tail structure remaining intact through the entire period when the CME should have been interacting with it. Either the magnetic field configuration in the tail was unusual, preventing reconnection, or the tail wasn't behaving like a typical plasma structure. Some researchers proposed that 3I, Atlas's low water abundance, might explain the non-response. Plasma tails derive from ionization of gas molecules, with water being a dominant contributor in most comets. If 3I, Atlas, was producing minimal water vapor, perhaps its plasma tail was too tenuous to interact strongly with the CME. However, MAVEN's detection of the large hydrogen cloud suggested substantial gas production, even if water specifically was scarce. The hydrogen should have been ionized by solar ultraviolet light and solar wind interactions, creating plasma that would respond to the CME. Alternative hypotheses invoked unusual magnetic field topologies around the comet. If the object somehow generated or maintained a magnetic field structure different from typical comets, it might shield the plasma tail from CME impacts. However, comets don't generate their own magnetic fields. They lack the iron cores and dynamo processes found in planets. The magnetic fields in cometary environments come from the solar wind itself, draped around the obstacle created by the gas and plasma clouds. Creating a configuration that could resist CME disruption required mechanisms that weren't part of standard cometary physics. The October CME event became another data point in the growing catalogue of 3I Atlas anomalies. An interaction that should have occurred, predicted with confidence based on decades of observations of solar wind-comet interactions, failed to materialize. The object's plasma environment appeared decoupled from the solar wind in ways that violated established understanding of how these systems behaved. As 3I, Atlas, continued its outbound journey, researchers were left questioning whether the classification as a comet remained appropriate for an object that systematically refused to behave like one. Inside the spectroscopic contradiction. Spectroscopy provides the most direct window into a comet's composition, revealing which molecules are present in the gas cloud surrounding the nucleus through their unique emission signatures. When sunlight strikes molecules in the coma, it excites electrons to higher energy states. As these electrons fall back to lower states, they emit photons at specific wavelengths determined by the molecule's structure. Each chemical species produces a distinctive pattern of emission lines, creating a fingerprint that identifies what's present and in what quantities. For 3I, Atlas, multiple high-resolution spectrographic surveys produced results that contradicted nearly every expectation about interstellar cometary composition. The James Webb Space Telescope's near-infrared spectrometer observed 3I Atlas during August, capturing data across wavelengths where numerous molecular emission features should appear. Water ice, when heated, produces strong emission lines in several infrared bands. The JWST spectrum showed these water features at levels barely above instrumental noise. Quantitative analysis, comparing the measured line strengths to laboratory standards and theoretical models, indicated water vapor contributed approximately 4% to the total gas mass in the coma. This fraction stood in stark contrast to solar system comets, where water typically dominates, accounting for 70 to 90% of outgassed material. Carbon monoxide and carbon dioxide, the next most abundant volatiles in typical comets, appeared in the JWST spectrum, but again at lower than expected levels. Carbon monoxide's strongest emission lines, located near 4.67 micrometers, showed intensities suggesting a production rate modest compared to the object's total gas output. Carbon dioxide features near 3 microns were similarly subdued. Combined, carbon-bearing molecules accounted for roughly 20% of the detected gas, leaving a substantial fraction of the coma's composition unidentified by standard molecular searches. Ground-based telescopes, equipped with high-resolution optical spectrographs, added complementary data. The Very Large Telescope's UVES instrument captured the visible wavelength region where emission from various molecular fragments and atomic species appear. Searches for CN, C2, and C3 molecular fragments commonly detected in comet comae and used as tracers of parent molecule abundances yielded weak detections. The ratios between these species deviated from the typical patterns seen in solar system comets, suggesting either different parent molecule compositions or unusual photochemical processing in the coma. One of the most surprising findings came from searches for ammonia and methane. These molecules, frozen at interstellar temperatures, should sublime readily as the comet approached the Sun. Ammonia, particularly, was expected to be abundant, given its common presence in icy bodies throughout the solar system. Yet the spectroscopic searches found no convincing ammonia emission lines. Upper limits placed its abundance well below predictions based on standard interstellar ice composition models. Methane similarly showed minimal presence, detected only weakly if at all depending on which observation set was analysed. The nickel detection added another layer of mystery. Optical spectroscopy revealed emission lines corresponding to neutral nickel atoms in the coma, a feature occasionally seen in solar system comets, but typically in trace amounts. In 3I, Atlas, the nickel emission was anomalously strong. Quantitative measurements of the line intensities indicated nickel abundances orders of magnitude higher than typical cometary values. The nickel-to-iron ratio, derived from comparing nickel emission lines to weak iron features in the same spectra, exceeded solar system norms by factors of 10 or more. Nickel in comets usually originates from refractory dust grains, solid particles containing metals that sublime at high temperatures. As the nucleus heats near the Sun, these grains release metallic vapors that produce atomic emission lines. The enhanced nickel abundance in 3I, Atlas, suggested either an unusual dust composition or temperatures high enough to vaporize nickel-rich materials preferentially. However, thermal models of the nucleus surface, based on its distance from the Sun and estimated albedo, predicted temperatures insufficient for efficient nickel sublimation. The metal's presence in such high abundance remained unexplained by conventional thermal processing. Alternative explanations for the spectroscopic anomalies focused on the object's formation environment. Interstellar ices form under conditions different from those in the solar system's protoplanetary disk. Temperatures in dense molecular clouds, where star and planet formation occurs, can drop to 10 degrees above absolute zero. At these extreme temperatures, gases freeze onto dust grains in different proportions than observed in solar system comets. Carbon monoxide becomes more abundant relative to water, and other volatile species show altered ratios. Perhaps 3I Atlas formed in such an environment, preserving a composition that reflected its interstellar origins. This formation scenario, while appealing, struggled to explain the near absence of water. Even in cold interstellar clouds, water ice is ubiquitous, coating dust grains and making up a substantial fraction of the ice mantles. Producing an icy body with only 4% water required special conditions, perhaps formation in a particularly carbon-rich region, or extensive processing by cosmic rays that altered the ice chemistry. Laboratory experiments attempting to recreate these conditions showed that while ice composition could be shifted, completely suppressing water formation proved difficult. The molecule forms too readily from the abundant hydrogen and oxygen in space. The spectroscopic data also revealed temporal variations that added complexity to composition analysis. As 3I Atlas rotated with its 16.16-hour period, emission line strengths fluctuated, indicating that gas production varied around the nucleus. Some regions appeared more active than others, releasing more gas when rotated into sunlight. However, the variations didn't follow simple patterns expected from a uniformly composed nucleus with localized active areas. Instead, different molecules showed production peaks at different rotation phases, suggesting compositional heterogeneity, different regions of the surface containing different ice mixtures. The hydrogen cloud detected by MAVEN gained new significance in light of the spectroscopic measurements. If water wasn't the hydrogen source, then where was it coming from? Molecular hydrogen, H2, is notoriously difficult to detect spectroscopically because it has no permanent electric dipole moment, making its emission lines extremely weak. The molecule could be abundant in the coma without producing obvious spectroscopic signatures. Some researchers propose that 3I Atlas might be outgassing molecular hydrogen directly, a scenario unprecedented in cometary science, but not physically impossible if the object had trapped H2 during formation in a cold interstellar environment, what the amateur images actually captured. Between the second and third weeks of observation windows, amateur astronomers worldwide began posting images that revealed details NASA's official gallery had missed. These weren't casual snapshots, they represented sophisticated observing campaigns, using equipment that, while modest compared to space telescopes, was optimized for the specific challenge of imaging faint, extended cometary features. The most successful images came from cooled CCD cameras and modern CMOS sensors attached to telescopes ranging from 10 to 20 inches in aperture, using integration times of several hours to build up signal from the faint coma and tail structures. The consistency across independent observations was immediately striking. From observatories in Spain, observers captured 3I Atlas, showing a bright, compact coma with multiple distinct jets radiating from the center. In Arizona, another observer using a 16-inch astrograph recorded the same jet structure, with 4 to 5 separate streams visible extending from the nucleus. Australian amateur astronomers, working during different rotation phases of the comet, imaged similar features but with the jets oriented at different angles relative to the tail, evidence that the object's rotation was carrying active regions across the field of view. Japanese observers added time series data, capturing how the jet's brightness varied over rotation periods. The jet morphology in these amateur images contradicted the blurred, unresolved views from some professional facilities. Each jet appeared as a narrow, well-defined stream, maintaining its structure over vast distances. Image processing revealed that these jets extended for hundreds of thousands of kilometers, far beyond the central coma, without significant spreading or diffusion. The sharpness of these features indicated that whatever was producing them was creating highly collimated flows, gas and dust streams confined to narrow angles, rather than spraying in all directions like typical cometary fountains. Advanced processing techniques allowed amateur astronomers to enhance subtle details in the tail structure. Digital filters that suppressed background stars while preserving extended nebulosity revealed intricate patterns in the dust tail, thin streamers and braided structures suggesting complex dynamics in how dust particles were being released and transported. Some images showed what appeared to be disconnected tail segments, regions where the tail's continuity broke, leaving gaps between the main structure and more distant material. These features resembled the tail disconnection events observed in other comets, but occurring without obvious solar wind disturbances to trigger them. Photometric measurements extracted from amateur images provided quantitative data on brightness variations. By measuring the intensity of light from different parts of the coma and tail over time, observers constructed light curves showing how the object's appearance changed with rotation. The data revealed a rotation period consistent with professional measurements, approximately 16 hours, but also showed that brightness variations weren't symmetric. As the nucleus rotated, bringing different hemispheres into view, the brightness fluctuated by amounts larger than expected from simple shape changes alone, suggesting active regions concentrated on specific parts of the surface. The color information in some amateur images added another dimension to analysis. Observers using LRGB filters or narrowband imaging captured the comet in different wavelength bands, allowing comparison of how the coma and jets appeared in blue versus red light. The jets showed color gradients, appearing bluer near the nucleus and redder farther out, a pattern consistent with dust particles of different sizes being carried at different speeds by the gas flow. Smaller particles, more easily accelerated, travelled faster and appeared closer to the nucleus, while larger particles lagged behind. These color distance relationships provided clues about the size distribution of dust being released. Perhaps the most remarkable amateur contribution came from coordinated observing networks. Groups of astronomers, organized through online forums, scheduled simultaneous observations from different longitudes, ensuring continuous coverage as Earth's rotation would otherwise cause gaps in monitoring. This coordination produced time series data spanning multiple days, capturing how 3I, Atlas's appearance, evolved with unprecedented temporal resolution. The continuous coverage revealed rapid changes in jet activity, features brightening and fading over periods of hours that might have been missed by observations separated by longer intervals. Technical analysis of the amateur images revealed why they succeeded where some larger facilities struggled. The combination of excellent seeing conditions, atmospheric steadiness that determines image sharpness, and long integration times allowed accumulation of photons from faint features that shorter exposures missed. Many of the most successful images came from remote observing sites chosen specifically for dark skies and stable air, factors that can matter more than aperture size for imaging extended, low-surface brightness targets like Comet Comae. The image processing workflow used by advanced amateurs incorporated techniques originally developed for professional astronomy. Dark frame subtraction removed instrumental noise patterns, flat fielding corrected for uneven illumination across the detector, and bias frame subtraction eliminated readout artifacts. These calibration steps, combined with careful stacking of multiple exposures to improve signal-to-noise ratio, produced images that approached professional quality. Software packages allowed precise alignment of frames despite the comet's motion against background stars, ensuring that the faint tail structure added constructively rather than blurring during the stacking process. Some amateur images captured 3I, Atlas, against fields of distant galaxies, providing cosmic context that highlighted the visitor's nature as an object from beyond our solar system. These compositions, showing the comet with its jets and tail superimposed on galaxy clusters millions of light years away, became powerful visualizations of the intersection between local solar system dynamics and the larger galactic environment. The images resonated beyond the astronomy community, illustrating in a visceral way that interstellar space isn't empty but contains bodies that occasionally cross paths with our sun. The amateur astronomy campaign demonstrated that citizen science contributions to professional research extended beyond data collection to include discovery-grade observations. Several features visible in amateur images prompted follow-up observations by professional facilities, directing telescope time toward investigating specific anomalies or testing hypotheses about the jet formation mechanisms. This collaboration between amateur and professional astronomers exemplified how modern astronomical research increasingly relies on distributed observation networks rather than single facilities, particularly for transient phenomena like cometary visitors that require rapid response monitoring across wide geographic distributions. The rotation problem no one wants to discuss. Photometric monitoring campaigns during July and August produced an unusually precise measurement of 3I, Atlas's rotation period, 16.16 hours, with uncertainties of only a few hundredths of an hour. This figure wasn't an estimate. It represented the result of careful analysis of brightness variations recorded over multiple rotation cycles, with different observatories independently confirming the same periodicity. Light curves showed the characteristic double-peaked structure expected from an elongated body tumbling through space, with brightness maxima occurring twice per rotation as the object presented its broadest cross-section toward Earth, and brightness minima when it rotated edge-on. This rotation period became the foundation for all subsequent physical modelling of the object, with 16.16 hours as a fixed parameter. Calculations of how surface features should evolve and how material escaping from the nucleus should distribute in space became deterministic. The physics left no ambiguity about expected outcomes. Any jet of gas and dust ejected from a specific location on the surface would trace a path through space determined by the outflow velocity and the rotation carrying its source around the nucleus. Over the roughly 29 days required for particles to travel 1 million kilometers at typical outflow speeds of 400 meters per second, the nucleus would complete approximately 43 full rotations. The geometry of rotating jet sources has been studied extensively in the context of solar system comets. When a vent or active area on a spinning nucleus releases material, that material carries angular momentum imparted by the rotating source. The result is a spiral pattern where the jet curves in the direction opposite to the rotation. For a nucleus rotating every 16 hours and ejecting material at 400 meters per second, the predicted spiral pitch, the angle at which the jet deviates from straight radial outflow, can be calculated from basic mechanics. The formula depends on the rotation period. the distance from the rotation axis to the vent, and the outflow velocity. For 3I, Atlas's measured parameters, this calculation predicted that jets should show clear curvature, bending by angles of tens of degrees over distances of hundreds of thousands of kilometers. The effect should be unmistakable in images that captured the full extent of the jets. Yet the November images showed jets that remained straight across distances exceeding 1 million kilometers. The observed geometry violated the predictions by margins too large to dismiss as measurement uncertainty or data processing artifacts. The jets should have been curved, they were not. Several escape mechanisms were proposed to reconcile the straight jets with the confirmed rotation period. One suggestion involved polar jets' active regions, located exactly at the rotation poles, where rotational velocity is zero. A vent at the pole would eject material radially outward without any rotational deflection, producing straight jets regardless of the nucleus's spin rate. However, this explanation required all the observed jets to originate from polar regions, a geometric configuration inconsistent with the images showing jets at various angles to the rotation axis as the object tumbled. Moreover, polar regions receive less solar heating than equatorial areas, making them less likely to host vigorous outgassing activity. Another proposal invoked rapid precession, a wobbling of the rotation axis similar to a spinning top. If the nucleus's rotation axis itself rotated around a different axis on short timescales, it might somehow average out the expected spiral signature in the jets. Detailed modelling of this scenario showed that while precession could modify the jet appearance, it couldn't eliminate the spiral structure entirely. The predicted modification would make the spirals more complex, not remove them. Furthermore, no observational evidence supported rapid precession. The light curves were consistent with simple rotation around a stable axis. The possibility of extremely fast outflow velocities was examined next. If gas and dust left the nucleus at speeds much higher than the typical 400 meters per second, the material would traverse large distances in shorter times, completing its journey before the nucleus rotated significantly. Pushing the required velocity revealed the problem with this explanation. Achieving straight jets to 1 million kilometers required outflow speeds approaching several kilometers per second velocities that cometary outgassing mechanisms couldn't generate. Thermal energy from solar heating produces gas expansion velocities determined by temperature and molecular weight. Even under the most optimistic assumptions about surface temperatures and light molecule species, the predicted speeds fell far short of what was needed to escape rotational deflection. The rotation problem extended beyond just the jet's appearance. Time series photometry revealed that brightness variations with the 16.16-hour period persisted throughout the observation campaign, showing no evidence of spin down or spin up. For the jets to remain straight while the nucleus rotated normally, some mechanism would need to either produce new jets at different locations each rotation cycle to maintain the same apparent direction in space, or confine the outflow through structures that physically constrained the gas and dust trajectory. The former required an implausibly organized pattern of surface activity, while the latter demanded physical structures, nozzles, channels, or magnetic fields not found in natural comets. Electromagnetic confinement emerged as a speculative explanation. If the gas in the jets was highly ionized, and if magnetic fields somehow existed around the nucleus, these fields might channel the plasma along field lines, maintaining straight trajectories despite rotation. However, this scenario faced multiple objections. First, cometary gas is typically neutral near the nucleus, becoming ionized only after traveling some distance into sunlight. Second, Comets don't generate their own magnetic fields. They lack the dynamo processes that require metallic cores and convection. Third, even if fields existed, confining neutral dust particles, along with ionized gas, required forces that magnetic fields alone couldn't provide. Laboratory experiments attempting to reproduce the straightjet phenomenon under controlled conditions met with consistent failure. Vacuum chamber tests at the Southwest Research Institute spun ice and dust mixtures while simulating solar heating. Jets formed as the ice sublimated, but they invariably showed the predicted spiral structure. Varying the rotation rate, the outflow velocity, and the surface properties changed the spiral's pitch and appearance, but never eliminated it. The experiments confirmed that standard physics couldn't produce straight jets from rotating sources under conditions relevant to cometary outgassing. Computer simulations provided another testbed for theories. Particle trajectory codes traced the paths of millions of individual dust, grains, and gas molecules ejected from rotating nuclei, accounting for gravity, radiation pressure, and gas drag forces. The simulations produced visualizations of jet morphology under various assumptions about rotation states, outflow patterns, and nucleus shapes. In no configuration did the simulations reproduce straight, undeflected jets extending to million-kilometer scales from a body spinning with a 16-hour period. The physics was unambiguous. Rotation should produce curvature, and the predicted curvature was absent from observations. Punch's stubby tail and what it hides. The polarimeter to unify the corona and heliosphere mission, known as Punch, deployed its wide-field cameras to capture 3I, Atlas, against the backdrop of the inner solar system. These instruments were designed to track the solar wind and coronal structures, imaging faint diffuse features that extend across large angular scales. Between late September and early October, Punch recorded multiple observations of the interstellar visitor, showing it as a faint point source with a short, stubby tail structure extending anti-sunward. The tail's appearance immediately sparked discussion among the science team. It seemed truncated, abruptly ending rather than gradually fading as typical cometary dust tails do. Dust tails form through a well-understood process. Solar radiation pressure pushes dust particles released from the nucleus, causing them to lag behind in the comet's orbital path and creating the characteristic swept-back appearance. Larger particles, less affected by radiation pressure, curve more strongly along the orbit, while smaller particles are pushed more directly away from the Sun. The combination creates tails that can extend for millions of kilometers, gradually thinning and fading as particle density decreases with distance. Punch's images of 3I, Atlas, showed none of this gradual transition. The tails seemed to simply stop at a relatively short distance from the nucleus. The Punch team's initial assessment considered instrumental effects first. Wide-field imaging systems struggle with dynamic range, the ratio between the brightest and faintest features they can simultaneously capture. If the coma was very bright and the extended tail very faint, the imaging system might saturate on the bright coma while failing to detect the faint tail beyond a certain distance. Subsequent data processing attempted to correct for this possibility, applying high-pass filters to suppress the bright central region while enhancing faint extended structures. The processed images still showed a truncated tail, suggesting the feature was real rather than an artifact of detector limitations. Background subtraction introduced another potential source of confusion. The Punch cameras image large fields containing background stars, diffuse zodiacal light from dust in the solar system, and stray light from Earth and the Sun. Removing these backgrounds requires careful modeling and subtraction, processes that can inadvertently remove real signals if the background model isn't perfect. When faint tail structures have similar brightness levels to background variations, aggressive background subtraction can erase them. The Punch data processing pipeline used multiple background estimation techniques, and while the specific details affected the tail's apparent extent, all methods showed it shorter than typical cometary dust tails at comparable distances from the Sun. Image stacking provided a way to improve sensitivity to faint structures. By combining multiple exposures taken over time, random noise averages out, while persistent features add constructively, increasing signal-to-noise ratio. The Punch team stacked images from different observation epochs, carefully accounting for the comet's motion to keep it aligned across frames. The stacked images should have revealed faint tail extension if it existed below the detection limit of individual exposures. While stacking did show some enhancement of the tail structure, it remained stubbier than predictions based on typical dust production rates and radiation pressure effects. The truncated appearance raised questions about the physical processes governing dust emission and transport. One possibility involved the dust size distribution. If 3I, Atlas, was producing predominantly large particles, they would be less affected by radiation pressure and would fall back toward the nucleus more quickly after emission, rather than being swept into an extended tail. However, this scenario created tension with other observations. Ground-based photometry and spectroscopy suggested dust production rates typical for a comet of 3I, Atlas's size, and heliocentric distance. If that dust consisted of large particles, the total mass loss rate would be extremely high, depleting the nucleus on timescales shorter than the object's likely age. Another explanation focused on dust production variability. If outgassing and dust emission were highly episodic rather than steady, the tail might show gaps or shortened segments corresponding to periods of low activity. The stubby appearance in Punch images could represent a snapshot during a quiescent phase, with more extended tail material present during earlier active periods but having since dispersed. Testing this hypothesis required comparing Punch observations with images from other facilities taken at similar times. Ground-based observers did capture the comet during the Punch observing windows, and their images generally showed more extended tails, though exact comparisons were complicated by different sensitivities and wavelength coverage. Viewing geometry introduced additional complexity. The apparent length of a cometary dust tail depends strongly on the observing perspective, the angles between the Sun, comet, and observer. When Earth is nearly aligned with the Sun-comet direction, dust tails can appear foreshortened, looking shorter than they actually are in space. Punch's orbital position and the geometry during its observation epochs placed it at an angle where some foreshortening would occur. Detailed geometric models calculating the three-dimensional tail structure and projecting it onto Punch's viewing plane showed that foreshortening could account for some but not all of the discrepancy between the observed stubby tail and expectations. The question of whether Punch was seeing genuine physical truncation or an artifact of instrumental and geometric effects remained unresolved in early analysis. The mission team released preliminary findings acknowledging the tail's unusual appearance, while cautioning that the data was still being calibrated and that instrumental artifacts couldn't be fully ruled out. This cautious stance reflected the broader challenge of interpreting observations from instruments operating at the edge of their design specifications. Punch was optimized for imaging diffuse solar wind structures, not point source comets with narrow tails. Comparison with other spacecraft observations provided context. Lucy, observing from a vastly different location in the solar system, captured 3I Atlas with its own cameras and reported tail features that appeared to point in unexpected directions. including sunward-facing structures that defied normal cometary behavior. The discrepancy between Punch's stubby tail and Lucy's anomalous tail directions suggested that either the comet's dust environment was highly complex, varying rapidly in ways that different observations captured at different states, or that interpreting these observations required better understanding of how geometry and instrumental effects could mislead. The Punch observations of 3I Atlas became a case study in the challenges of multi-mission coordination and cross-validation, when different instruments viewing the same object from different vantage points produce conflicting results. Determining which observations accurately represent reality requires detailed modelling of each instrument's capabilities and limitations, careful geometric projections, and honest assessment of uncertainties. The stubby tail remained an open question, neither definitively real nor conclusively artificial, awaiting higher resolution follow-up observations that could resolve whether 3I, Atlas's dust environment, truly deviated from standard cometary behavior, or whether the initial observations had misled interpretations. Lucy's sunward feature and projection physics. Lucy spacecraft cameras captured 3I Atlas on September 16th from a distance of approximately 240 million miles. An observation made during the spacecraft's cruise through the outer solar system en route to its primary mission targets, Jupiter's Trojan asteroids. The image revealed a faint streak extending from the comet's nucleus. But its direction was wrong. It pointed toward the Sun rather than away from it. This sunward-facing feature contradicts the fundamental behavior that defines cometary tails. Material pushed away from the Sun by radiation pressure and solar wind forces invariably create structures pointing anti-sunward. The Lucy team's image immediately generated confusion and intense scrutiny about whether the observation represented genuine physics or geometric illusion. Cometary tails come in two varieties. Dust tails consist of solid particles released from the nucleus and pushed anti-sunward by solar radiation pressure, creating curved structures that follow the comet's orbital path. Iron or plasma tails form from ionized gas molecules swept directly away from the Sun by the solar wind's magnetic field, producing straight tails pointing exactly opposite the Sun's direction. Both tail types, while differing in morphology and composition, share the fundamental property of extending anti-sunward. A sunward-pointing tail violates these established principles, requiring either exotic physics or misinterpretation of the observational geometry. The Lucy science team's initial analysis focused on projection effects, geometric configurations, where three-dimensional structures can appear to point in misleading directions when projected onto a two-dimensional image. Plane. The most relevant case is the anti-tail, a phenomenon where dust particles spread along the comet's orbital plane create an apparent tail-like structure pointing sunward when Earth, or in this case, Lucy, lies nearly in that plane. The effect results from perspective. Dust particles trailing behind the comet in its orbit, when viewed from certain angles, appear to extend forward toward the Sun due to the projected geometry. Detailed calculation of the viewing geometry during Lucy's observation date provided a test of the anti-tail explanation. On September 16th, Lucy's position relative to 3I, Atlas, and the Sun created specific angles that could be compared to conditions known to produce anti-tail appearances in solar system comets. The orbital plane of 3I, Atlas, its position along that orbit, and Lucy's location in space defined the three-dimensional configuration. Geometric projection calculations showed that the viewing angle was indeed favourable for an anti-tail effect. Lucy was positioned such that the comet's orbital plane projected nearly edge-on, the exact configuration needed to see trailing dust particles appearing to point sunward. However, the anti-tail explanation required certain conditions to be met. First, the comet needed to have released dust particles along its orbital path, creating the sheet of particles necessary for the effect. Second, these particles needed to be spread in the orbital plane rather than broadly distributed in all directions. Third, the observed feature's brightness should match predictions for sunlight scattering off dust particles at the calculated distances and angles. The Lucy team's photometric analysis of the sunward feature addressed these requirements, measuring its brightness and comparing it to models of dust particle light scattering. The calculated brightness proved problematic. Anti-tails from dust particles typically appear fainter than the main dust tail because the scattering geometry for sunward viewing is less favourable than for anti-sunward viewing. Lucy's image showed the sunward feature with similar or even slightly greater brightness than other tail structures visible in the same frame. This brightness anomaly suggested either an unusually large amount of dust distributed along the orbit or forward scattering effects enhancing the sunward feature's visibility beyond typical levels. Both possibilities required assumptions about dust, properties, size distribution, and composition that weren't well constrained by other observations. An alternative explanation invoked jets pointing sunward. If the nucleus had active regions on its sun-facing side, ejecting material with sufficient velocity to overcome gravity and radiation pressure, these jets could create the appearance of a sunward extending feature. However, this scenario faced significant objections. The forces required to push dust particles sunward against radiation pressure would demand outflow velocities far exceeding normal cometary outgassing speeds. While gas molecules can achieve high velocities through thermal acceleration, dust particles are too massive to be efficiently accelerated by gas drag to the required speeds. The physics of cometary outgassing doesn't support sustained sunward dust jets. Time domain considerations added another constraint. The Lucy image represented a snapshot at a single moment, while the sunward feature's appearance should vary with the comet's rotation and viewing geometry. Subsequent observations from other facilities around the same date showed predominantly anti-sunward tail structures without prominent sunward features. This discrepancy suggested that Lucy had captured either a transient event, a short-lived burst of material, or a feature whose visibility was highly dependent on the specific viewing geometry that Lucy alone provided at that moment. The Lucy team's published analysis acknowledged multiple possibilities while favouring the projection effect explanation. Their report emphasised the challenges of interpreting features in images of distant, faint objects observed from unusual vantage points. They calculated error bars on the feature's brightness and position, noting that uncertainties in background subtraction and the comet's exact location affected the reliability of detailed interpretations. The sunward feature remained labelled as under investigation, a diplomatic acknowledgement that the observation was intriguing but not definitively explained. Comparison with historical observations provided context. Several solar system comets have shown apparent sunward features in specific viewing geometries, most famously Comet Aaron-Rowland in 1957, whose dramatic anti-tail was captured by photographers worldwide. In each case, careful geometric analysis confirmed projection effects rather than truly sunward material flow. The 3I Atlas observation fit this historical pattern, an initially puzzling feature that likely resulted from viewing geometry rather than exotic physics, but with enough ambiguity to prevent definitive closure without additional data from different viewing angles. The Lucy observation became emblematic of broader challenges in characterizing 3I Atlas. With only limited observation opportunities from spacecraft positioned throughout the solar system, each viewing angle provided unique but incomplete information. Reconciling contradictory appearances, Punch's stubby tail, Lucy's sunward feature, and ground-based observations of normal anti-sunward tails required piecing together a three-dimensional picture from two-dimensional snapshots taken from widely separated vantage points. The process highlighted how multi-mission coordination, while providing diverse data, also created interpretation challenges when different instruments with different capabilities observed the same target under different conditions. The water, desert, and hydrogen factory. Water defines cometary identity in solar system objects. The very classification of an object as a comet rests heavily on detecting water-ice sublimation as it approaches the Sun, producing the characteristic coma and tail structures that distinguish comets from inert rocky asteroids. For 3I, Atlas, this fundamental expectation collapsed under spectroscopic scrutiny. Multiple independent observation campaigns using different instruments and techniques converged on an uncomfortable conclusion. Water vapor, the dominant volatile in every well-studied solar system comet, was almost entirely absent from this interstellar visitor's gas production. The James Webb Space Telescope's near-infrared observations targeted specific wavelength regions where water molecules produce their strongest emission features. When solar ultraviolet light excites water molecules in a cometary coma, they emit characteristic photons at wavelengths near 2.7 micrometers and other near-infrared bands. JWST's spectroscopic data showed these water emission features at levels barely distinguishable from instrumental noise, weak signals that quantitative analysis translated into water abundance, estimates of approximately 4% of the total gas composition. For context, water typically comprises 70 to 90% of outgassed material from solar system comets at comparable solar distances. Ground-based facilities corroborated the water deficit. The Very Large Telescope's high-resolution spectrographs searched for hydroxyl OH emission lines in the ultraviolet and visible regions. Hydroxyl radicals form when solar photons break apart water molecules through photodissociation, creating one of the most reliable traces of water presence in cometary comae. The VLT data showed weak OH emissions requiring production rates orders of magnitude below what would be expected for a comet of 3I, Atlas's size and activity level. Cross-checking with other water-related species oxygen atoms from further dissociation and vibrationally excited water molecules yielded consistent results pointing to extreme water depletion. This water scarcity created immediate tension with other observations. MAVEN's ultraviolet spectrograph had detected a massive hydrogen cloud extending 33,000 miles from the nucleus. Hydrogen production at the observed levels, approximately 1028 atoms per second based on Lyman alpha brightness measurements, traditionally implies substantial water sources. The standard photochemical pathway starts with water molecules escaping the nucleus, which then photodissociate in sunlight to produce hydrogen atoms. MAVEN's detected hydrogen production rate, when traced backward through this pathway, predicted water outgassing rates at least 10 times higher than the spectroscopic observations actually found. The mathematical contradiction was inescapable. Either the hydrogen wasn't coming from water, or massive amounts of water were present but somehow evading spectroscopic detection. The latter possibility faced significant obstacles. Water's spectroscopic signatures are well understood and arise from fundamental molecular physics that doesn't vary with circumstances. Hiding water in quantities sufficient to explain the hydrogen production would require the gas to remain in states that didn't produce detectable emissions. Either extremely cold molecular gas that wasn't excited by sunlight, or water distributed in forms that weren't accessible to spectroscopic observation. Alternative hydrogen sources became necessary considerations. Molecular hydrogen, H2, could in principle be outgassed directly from the nucleus if it had been trapped in ice structures during the object's formation. Interstellar environments at temperatures near absolute zero allow hydrogen to condense onto dust grains and potentially become incorporated into ice mantles. However, hydrogen's small size and high volatility make it difficult to retain even in the coldest ices. Laboratory experiments showed that H2 trapped in water ice or other frozen matrices escapes readily when temperatures rise above about 20 Kelvin. Keeping hydrogen trapped until 3I, Atlas, reached the inner solar system, where surface temperatures exceed 200 Kelvin, required special conditions not readily explained by standard interstellar ice chemistry. Organic molecules offered another potential hydrogen reservoir. Hydrocarbons and other carbon-hydrogen compounds, when photodissociated by solar ultraviolet radiation, release hydrogen atoms that could contribute to the observed cloud. The spectroscopic surveys did detect some organic species emission lines corresponding to carbon-bearing molecules like CN and C2, but their abundances were insufficient to account for the hydrogen production rates. Detailed photochemical modelling calculated how much hydrogen would be released from the observed quantities of organics through known photodissociation pathways. The answer fell short by at least an order of magnitude. The organic molecules simply weren't abundant enough to be the primary hydrogen source. Subsurface reservoirs presented a more exotic possibility. If the nucleus contained deep layers of water ice that were somehow shielded from spectroscopic observation, perhaps by being too cold to sublime efficiently or covered by a thick insulating dust layer, this hidden water could sublime. Slowly, with the released water molecules immediately photodissociating near the surface before producing detectable emissions in the coma. In this scenario, hydrogen atoms would be created close to the nucleus, then expanding outward to create the observed cloud, while water molecules never accumulated in sufficient densities at observable distances to produce strong spectroscopic signatures. Testing this hypothesis required modelling the thermal structure of the nucleus interior, calculating sublimation rates from buried ice, and predicting where photodissociation would occur. The thermal models proved discouraging for the hidden water hypothesis. At 3I, Atlas's perihelion distance of approximately 0.8 AU from the Sun, surface temperatures reach levels sufficient to sublime water ice vigorously. For substantial ice to remain inactive, it would need to be buried beneath meters of insulating material dust or refractory crust thick enough to prevent heat penetration. However, such thick crusts typically suppress all volatile release, not just water's visible emissions. If ice layers deep enough to be thermally shielded were outgassing, the overlying material would need gas permeability, allowing hydrogen escape while somehow preventing water molecular escape. No laboratory experiments or observations of solar system comets showed precedent for this kind of selective permeability. Photodissociation timescales added another constraint. Water molecules released from a cometary nucleus survive, on average, about 80,000 seconds in sunlight before photodissociating into hydrogen and oxygen. At typical expansion velocities of 1 kilometer per second, this survival time allows water molecules to travel roughly 80,000 kilometers before breaking apart distances well within the observable coma and within the regions surveyed by spectroscopic instruments. For water to escape detection while contributing to hydrogen production, it would need to photodissociate on much shorter timescales, or be confined to regions very close to the nucleus, where observing conditions made spectroscopy difficult. Neither scenario fits the observed data cleanly. The water-hydrogen paradox became one of 3I, Atlas's most perplexing anomalies. It represented not just a surprising compositional oddity, but a fundamental challenge to understanding what material composed the object and what processes were governing its gas production. Every attempt to reconcile the low water detection with the high hydrogen production introduced new assumptions that lacked independent verification. The possibility that this interstellar visitor represented a class of object with composition radically different from solar system comets gained traction not because it was well supported by theory, but because it was the remaining option after standard explanations failed: the nickel anomaly and metal vapor physics. Optical spectroscopy of cometary comae typically reveals emission lines from common molecular fragments and atoms: sodium, iron, magnesium, calcium, and various carbon-bearing species. These elements originate from dust grains in the coma solid particles that sublime at high temperatures, releasing metal vapors that produce atomic emission when excited by sunlight. The relative abundances of different metals in cometary gas roughly match solar system average compositions, reflecting the materials that condensed in the protoplanetary disk billions of years ago. Nickel appears in these spectra, but usually as a trace constituent, with emission lines significantly weaker than iron's lines. For 3I Atlas, this normal pattern was inverted. Nickel emission dominated over iron in ways never observed in solar system comets. The nickel detection came from multiple high-resolution optical spectrographs, including instruments on the Very Large Telescope and the Keck Observatory. These facilities captured spectra covering wavelength regions where nickel atoms produce characteristic emission lines, particularly features near 3,000, 400 and 3,500 angstroms. Measuring emission line intensities allowed calculation of nickel abundance in the coma relative to other species. The results were startling. Nickel to iron ratios exceeded solar system values by factors of 10 or more. In quantitative terms, whereas typical comets show nickel contributing perhaps a few percent of the metal vapor emissions, 3I Atlas showed nickel dominating, with iron relegated to minority status. This compositional anomaly demanded explanation through the physics of metal sublimation and grain chemistry. In cometary comae, metal atoms originate from refractory dust particles, solid grains with high melting and sublimation temperatures that can withstand solar heating without immediately vaporizing. As these grains warm in sunlight, their surfaces begin releasing vapors, with different elements subliming at temperatures determined by their vapor pressures and bonding strengths in the grain matrix. Iron, with a relatively high sublimation temperature, typically requires surface temperatures above 1,300 Kelvin to produce significant vapor pressure. Nickel's sublimation temperature is similar, creating no obvious reason for nickel to vastly outpace iron in gas phase abundance. The enhanced nickel to iron ratio suggested that 3I, Atlas's dust grains, had unusual composition metal abundances that deviated from solar system norms. This possibility raised questions about the object's formation environment. In stellar nucleosynthesis, the processes creating heavy elements produce iron and nickel in relatively fixed ratios determined by nuclear physics in supernovae and evolved stars. Deviations from these standard ratios require special circumstances, perhaps formation in an environment enriched in material from specific types of stars, or chemical fractionation processes that separated nickel from iron during dust grain condensation. Experimental studies of interstellar dust analogues provided some context. Laboratory simulations of dust grain formation under various conditions showed that temperature and pressure during condensation affect which elements incorporate preferentially into solid phases. At temperatures near 1500 Kelvin, typical of dust condensation in stellar outflows, iron and nickel tend to condense together into mixed metal grains or iron-nickel alloys. However, under lower temperature conditions, or in the presence of certain gas phase molecules, fractionation can occur, with one metal preferentially segregating. Whether such conditions existed in 3I, Atlas's formation environment, remained speculative, without knowledge of where and when the object formed. Alternative explanations focused on grain surface properties and sublimation kinetics. If dust grains had surface coatings or structures that selectively retained iron while allowing nickel to escape, this could create the observed nickel enhancement in the gas phase without requiring unusual bulk composition. Laboratory experiments on metal alloys showed that sublimation rates from solid surfaces depend on crystal structure, grain size, and surface chemical state. Under some conditions, elements with similar bulk volatilities can show different release rates from solid matrices due to diffusion barriers or preferential bonding sites. Whether these laboratory effects scaled to cometary dust grains under solar illumination conditions required extrapolation beyond experimentally tested regimes. The thermal environment of dust grains in 3I, Atlas's coma, added constraints. Grain temperatures depend on their size, composition, and distance from the nucleus. Smaller grains heat more efficiently in sunlight, reaching higher equilibrium temperatures than larger grains at the same heliocentric distance. If nickel-rich vapor production required temperatures at the high end of what grains achieved, then the size distribution of dust particles would affect the observed nickel abundance. Modelling grain temperatures for particles ranging from submicron to millimeter sizes, at distances from the nucleus spanning the optically thick inner coma to the transparent outer regions, showed temperature ranges from roughly 250 to 450 Kelvin at perihelion. These temperatures fall well below nickel's sublimation point under normal conditions, suggesting that simple thermal sublimation wasn't releasing nickel efficiently. Photochemical processes offered another pathway for metal release. When ultraviolet photons strike dust grain surfaces, they can break chemical bonds and eject atoms through photodesorption, essentially photoelectric effect for atoms bonded in solid lattices. This process doesn't require high temperatures. Instead, it depends on ultraviolet photon flux and the bond strength between surface atoms and the grain matrix. If nickel atoms were more loosely bound at grain surfaces than iron atoms, photodesorption could preferentially release nickel, creating the observed abundance anomaly. Testing this hypothesis required quantum chemistry calculations of metal surface binding energies in various grain materials, silicates, carbons, and mixed compositions under the radiation environment near the Sun. The nickel enhancement also raised questions about contamination or interference in spectroscopic measurements. Emission lines at similar wavelengths to nickel features could arise from other species, potentially creating false detections or exaggerated abundances. The spectroscopy teams addressed this concern through careful line identification, comparing observed wavelengths to comprehensive atomic databases and checking for coincidences with other possible emission sources. The analysis confirmed that the observed features matched nickel transitions uniquely, with no plausible alternative identifications at the required wavelengths and relative intensities. The nickel detection was robust, not an artifact of misidentified lines. Time-domain spectroscopy revealed variations in nickel emission strength correlated with 3I, Atlas's rotation period. As different parts of the nucleus rotated into sunlight, the intensity of nickel emission lines fluctuated, suggesting that dust production and metal vapor release varied around the surface. These variations provided indirect constraints on the distribution of nickel-rich material. If confined to specific active regions, the rotating nucleus would produce brightness modulations as those regions alternately faced toward and away from the Sun. The observed modulation patterns indicated that nickel sources were not uniformly distributed, supporting models where composition or grain properties varied across the nucleus surface. The nickel anomaly joined the water deficit and hydrogen excess as compositional puzzles that collectively suggested 3I, Atlas, represented a new class of object. Each anomaly individually could potentially be explained through special circumstances or measurement uncertainties. Together, they painted a picture of an interstellar visitor whose composition deviated systematically from solar system norms across multiple independent observables. Whether these deviations reflected exotic formation conditions in another star system, extensive alteration during interstellar travel, or something more fundamental about the object's nature, remained an open question as observations continued. The dust production mismatch. Dust production from cometary nuclei follows predictable patterns established through decades of observations. As sunlight heats the surface, ice sublimates, and the escaping gas drags dust particles into space. The ratio of dust mass to gas mass, often called the dust-to-gas ratio, varies among comets, but typically falls in a range from 0.1 to 10, meaning that for every kilogram of gas released, between 0.1 and 10 kilograms of dust escape as well. This ratio provides a diagnostic of the nucleus composition and physical structure. Higher ratios indicate dust-rich or depleted volatile surfaces, while lower ratios suggest cleaner ice with less refractory contamination. For 3I, Atlas, measuring the dust production rate and comparing it to gas production revealed another significant anomaly. Dust production rates can be estimated through photometry, measuring the total brightness of the coma and determining how much comes from sunlight scattered by dust particles versus gas emission. The scattered light component depends on the total dust cross-sectional area in the coma, which relates to both the number of particles and their size distribution. Observations at visual wavelengths captured primarily scattered sunlight from dust, allowing calculation of the total dust mass if assumptions about particle sizes and compositions were made. Standard models use dust grains with sizes ranging from submicron to millimeter scales, following size distribution laws derived from zodiacal light and meteor observations. Photometric observations of 3I, Atlas, during its perihelion passage, showed a moderately bright coma consistent with dust production rates of approximately several hundred kilograms per second. This estimate came with significant uncertainties, factors of 2 or 3 due to unknowns in particle size distribution and composition. However, even accounting for uncertainties, the inferred dust production suggested a modestly active comet, comparable to some but not all observed solar system comets at similar heliocentric distances. The brightness levels didn't indicate an exceptionally dust-rich object. They pointed to typical or even somewhat below average dust output. Gas production rates came from spectroscopic measurements and models. The detected molecular species, what little water was found, carbon monoxide, carbon dioxide, and others, each had measured production rates derived from emission line intensities. Summing these contributions gave a total gas production rate. For 3I Atlas, this calculation was complicated by the water deficit, with water contributing only a few % of the gas. Other molecules had to account for the majority. Carbon monoxide and carbon dioxide, detected through infrared spectroscopy, showed production rates of tens to perhaps 100 kilograms per second. Adding contributions from species not directly measured but inferred from photochemistry brought total gas production estimates to the low hundreds of kilograms per second range. Comparing these numbers, dust production of several hundred kilograms per second and gas production of similar magnitudes yielded dust-to-gas ratios near unity or slightly higher. This ratio was not dramatically unusual by solar system comet standards, sitting comfortably within the observed range. However, the comparison raised a subtle problem. The gas production was dominated by species that don't efficiently drag dust. Water vapor, being relatively light and achieving high velocities when sublimating from warm surfaces, efficiently entrains dust particles through drag forces as it flows away from the nucleus. Heavier molecules like carbon monoxide and carbon dioxide, while present, are less efficient at coupling to dust particles and accelerating them to escape velocity. The physics of dust entrainment depends on gas density, velocity, and the drag coefficient between gas molecules and dust particles. For a given gas production rate, replacing water with heavier molecules reduces the efficiency of dust ejection. Detailed models calculating dust trajectories under different gas compositions showed that achieving the observed dust production rates with 3I, Atlas's low-water gas mix, required either unusually small dust, particles easier to accelerate, or higher gas velocities than thermal sublimation typically provides. Neither condition matched other observational constraints. Dust size distributions inferred from scattered light, color, and polarization suggested normal particle sizes, and gas velocities measured through spectroscopic line widths were consistent with thermal speeds, not anomalously high values. This mismatch implied that dust ejection wasn't being driven primarily by sublimation drag, the standard mechanism for cometary dust release. Alternative dust ejection mechanisms include ice phase changes, where subsurface ice transitions from amorphous to crystalline structures and releases stored energy explosively, or gas pressure buildup beneath dust mantles that fractures the crust and ejects material. Both mechanisms had been invoked for solar system comets showing high dust production relative to gas. However, these processes typically produce episodic activity and outbursts, creating brightness variations and time-variable dust release. 3I, Atlas's photometric behavior, showed relatively smooth brightness evolution without clear outburst signatures. Another possibility involved extremely low gas-to-dust coupling efficiency. If most of the gas escaped through porous subsurface pathways without encountering dust particles at the surface, then drag forces would be minimal, and dust ejection would require different mechanisms. In this scenario, the observed dust might originate from localized active areas where surface conditions differed, exposed ice patches or fractures, where sublimation was vigorous enough to lift particles despite low water content. Distributing dust production among multiple discrete sources rather than continuous global sublimation could reconcile the observed dust rates with the measured gas composition, but required fine-tuning of surface properties and activity patterns. Observations attempted to resolve this question by searching for localized dust jets, narrow features indicating concentrated source regions. The amateur images showing distinct jets radiating from the nucleus supported the localized source hypothesis. If these jets represented the primary dust production sites, then calculating dust ejection rates from jet cross-sections and velocities could provide independent estimates to compare with photometric total dust production. The jet dimensions in the images, combined with assumed outflow velocities, suggested localized production rates that, when summed over visible jets, matched the photometric estimates within uncertainties. This consistency indicated that dust emission was indeed concentrated in active regions rather than distributed globally. The localized activity model created its own puzzles. If only specific areas produced dust efficiently, what made those regions different from inactive portions of the surface? Solar illumination patterns on a rotating nucleus create diurnal temperature cycles that should activate different regions as they rotate into sunlight. Yet the observed jets maintained stable orientations over rotation cycles, suggesting the active regions weren't simply whichever areas happened to face the sun at any moment. Perhaps compositional heterogeneity, patches of exposed ice interspersed with inactive dust-covered terrain, explained the localized activity. But this raised questions about how such patchiness could survive the approach to perihelion when heating should have been sufficient to activate even relatively refractory materials. The dust production mismatch joined the growing catalogue of features that individually might be explained through special circumstances, but collectively suggested 3I Atlas didn't conform to standard cometry behaviour. The object produced dust at rates inconsistent with its gas composition and gas production rates, required localized activity to concentrate dust ejection despite lacking clear triggers for such localization, and maintained this activity pattern consistently through perihelion passage. Each attempted explanation introduced new assumptions about surface properties, composition heterogeneity, or physical processes, assumptions that weren't independently verified and that strained credulity when compounded across all of 3I Atlas's anomalous characteristics, where 3I Atlas is actually going. Trajectory calculations for interstellar objects serve two purposes: determining where they came from and predicting where they're going. For 3I Atlas, the inbound trajectory analysis showed it arriving from a direction roughly toward the constellation Ursa Major, though without precise enough measurements to identify a specific source star system. The outbound trajectory carries more immediate interest. It determines what regions of the solar system the object will traverse, what future observation opportunities exist, and whether any planetary encounters lie ahead. Updated orbital solutions, incorporating all available tracking data through perihelion passage, paint a concerning picture of where this visitor is headed. The object's hyperbolic trajectory carries it outward from the Sun at an excess velocity of approximately 23 kilometers per second relative to the solar system's escape velocity. This speed places 3I Atlas among the faster interstellar visitors detected, moving considerably quicker than Comet Borisov, but still slower than Oumuamua's departure speed. At this velocity, the object will traverse the outer solar system relatively quickly by astronomical standards, crossing Neptune's orbital distance within a few years and reaching the heliopause, the boundary where the Sun's influence yields to interstellar space within a few decades. The outbound trajectory's orbital inclination, nearly 180 degrees, means 3I Atlas is moving retrograde relative to planetary orbits, travelling in the opposite direction from the planet's revolution around the Sun. This geometry makes planetary encounters less likely, since any close approach would involve very high relative velocities as the object passes planets moving the opposite direction along their orbital paths. However, the trajectory does carry 3I Atlas through regions populated by Kuiper Belt objects and other trans-Neptunian bodies, creating possibilities for close passes near these small, distant solar system members. Detailed trajectory propagation reveals that the outbound path passes relatively near Uranus's orbital path, though the timing ensures that Uranus itself will be far from the crossing point when 3I Atlas transits that distance. The minimum distance approach to Uranus's orbit occurs roughly 2028. With the planet positioned nearly opposite the crossing point, unfortunate timing that prevents a close flyby that might have provided additional gravitational deflection data and close-range observational opportunities. Similar analysis for Neptune's orbit shows even less favourable geometry, with the planet's position creating a missed distance of several AU at closest theoretical approach. The trajectory's orientation carries 3I Atlas toward the southern celestial hemisphere as viewed from Earth, progressively making observations more challenging from northern hemisphere facilities as the object recedes. By late 2026, prime observing sites shift to southern observatories facilities in Chile, South Africa, and Australia become critical for continued monitoring. This geographic constraint affects which telescopes can track the object and introduces scheduling challenges as the pool of available facilities narrows. The fading brightness as distance increases compounds these difficulties, with even large telescopes struggling to detect the object beyond certain distance thresholds. Predictions for future brightness evolution depend critically on uncertain parameters, the object's true size, its surface albedo, and whether outgassing activity will continue as it moves farther from the Sun. Standard models, assuming typical cometary sublimation, predict that activity should decline rapidly beyond approximately 2.5 AU, as surface temperatures drop below levels sufficient to sublime most volatiles. However, 3I Atlas's anomalous composition, particularly its low water content and enhanced nickel emission, complicates these predictions. If the object contains substantial amounts of supervolatile ices, species like carbon monoxide, that sublime at much lower temperatures than water activity, might persist to greater distances than typical comets maintain. Long-term trajectory stability calculations examined whether gravitational perturbations from outer planets could significantly alter the departure path. Jupiter, despite being massive, lies far from the trajectory and exerts minimal influence. Saturn, Uranus, and Neptune similarly contribute negligible perturbations due to large minimum distances. The dominant gravitational influence post-perihelion is the Sun itself, gradually decelerating the object's outward motion without substantially changing its direction. Barring unexpected encounters with unknown massive bodies in the outer solar system, a 3I Atlas will follow a nearly straight-line path in heliocentric coordinates once well beyond planetary distances. The trajectory carries concerning implications for future observation planning and potential hazard assessment. As the object recedes, opportunities for detailed characterization diminish. Spectroscopic measurements require brightness levels that fall below detection thresholds as distance increases and activity potentially ceases. The window for answering outstanding questions about composition, structure, and the mechanisms behind observed anomalies closes within a few years at most. Beyond that, 3I Atlas becomes a fading point of light, eventually invisible even to the largest telescopes, carrying its mysteries back into interstellar space. Projection into the distant future shows 3I Atlas eventually crossing into interstellar space with a velocity vector relative to nearby stars. Its trajectory will carry it toward regions of the galaxy currently populated by stars at distances of tens to hundreds of light-years from the Sun. Whether it will ever encounter another stellar system depends on the local stellar density and dynamics factors that create low but non-zero probabilities of future captures or close passes. From the perspective of future inhabitants of those hypothetical systems, 3I Atlas might someday become their own interstellar visitor, arriving with whatever secrets it retained from its passage through our solar system. The most immediate concern involves observation planning for the remaining accessible period. Telescope allocations prioritize targets based on scientific return and feasibility. 3I, Atlas, represents a unique target, one of only 3 confirmed interstellar visitors, and the first showing such extreme compositional and behavioral anomalies. However, its fading brightness and challenging southern hemisphere position compete with other scientific priorities for limited telescope time. Coordination among international facilities becomes critical to ensure continued monitoring through the final months of viable observation before the object fades beyond reach, taking answers to its anomalies with it into the darkness beyond our planetary neighbourhood. The observational window that's closing. Distance creates an unforgiving deadline for astronomical observations. As 3I Atlas recedes from the Sun, the solar flux illuminating its surface decreases. Following an inverse square law, moving twice as far from the Sun means receiving 1/4 the sunlight. For objects whose visibility depends on sunlight reflection or fluorescent emission excited by solar radiation, this fading is inexorable. Simultaneously, the object's distance from Earth increases, creating additional dimming as the apparent brightness falls following another inverse square relationship with distance from the observer. These combined effects shrink the reflected light reaching Earth's telescopes rapidly, making every passing month significantly degrade observing conditions. Photometric predictions based on standard cometry activity models suggested that 3I Atlas would remain detectable to large ground-based telescopes through mid-2026, with brightness fading below 20th magnitude, the practical limit for spectroscopic observations by late that year. These predictions assumed typical water-ice-driven activity, declining as surface temperatures dropped below water sublimation points around 2.5 AU heliocentric distance. However, 3I Atlas's unusual composition and demonstrated non-standard behavior introduced uncertainties into these forecasts. If supervolatile ices continued outgassing at greater distances, the object might maintain detectable activity longer than predicted. Conversely, if dust production ceased abruptly, or if the low water content implied minimal activity potential overall, fading might occur faster than models suggested. Actual brightness measurements through late 2025 and into 2026 showed the object dimming roughly consistent with predictions, neither dramatically exceeding expectations nor fading precipitously. This behavior allowed observers to plan campaigns with reasonable confidence in brightness forecasts several months ahead. However, the margin for error narrowed continuously. An unexpected dimming event, whether from cessation of activity or unfavorable changes in viewing geometry, could render the object unobservable with little warning. This uncertainty drove efforts to obtain critical observations sooner rather than later, prioritizing data types most sensitive to faintness and therefore earliest to become impossible. Spectroscopic observations faced the strictest brightness requirements. Spreading an object's light across multiple wavelength channels to measure spectral features demands more photons than simple imaging photometry. High-resolution spectroscopy, necessary for detecting weak emission lines and measuring velocity-resolved line profiles, required the brightest possible targets. For 3I Atlas, high-resolution spectroscopic viability expired first, with useful signal-to-noise ratios becoming unattainable as brightness dropped below approximately 18th magnitude. Medium and low-resolution spectroscopy extended the observational window by another magnitude or two. But even these techniques faced limitations as faintness increased integration times to impractical durations. Imaging remained viable to fainter limits, with large telescopes capable of detecting 3I Atlas as a point source to perhaps 23rd or 24th magnitude under excellent conditions. However, detectability didn't equate to scientific utility. Resolved imaging of coma structure and jets required sufficient brightness to reveal extended features against sky background, a more stringent requirement than mere detection of the nucleus as a point source. By the time the object faded to magnitudes accessible only through deep imaging, structural details would be lost, limiting observations to astrometry, position measurements, and basic photometry without the morphological information that had proven so puzzling and important during brighter phases. Space-based observations offered certain advantages over ground-based facilities. The Hubble Space Telescope and James Webb Space Telescope, operating above Earth's atmosphere, avoided seeing limitations and achieved diffraction-limited resolution and sensitivity unavailable from the ground. However, these premier facilities faced intense competition for observation time, with 3I, Atlas, competing against proposals targeting distant galaxies, exoplanets, and other high-priority scientific objectives. Securing additional observation time required compelling scientific justifications, demonstrating that observations would answer specific questions rather than merely adding incremental data to already obtained measurements. The James Webb Space Telescope faced particularly tight scheduling constraints. Its observing calendar was planned months in advance, with every hour allocated to specific programs. Requesting directors discretionary time for target of opportunity observations of 3I, Atlas required making the case that the object represented a sufficiently unique and time-critical target to justify displacing other approved programs. The bar for such requests was high, granted primarily for transient events like supernovae or unexpected phenomena with narrow observation windows. Whether 3I, Atlas's anomalies, met this threshold remained a subject of debate within the astronomical community. Coordination among ground-based facilities attempted to maximize scientific return from the closing observational window. The International Astronomical Union's Central Bureau for Astronomical Telegrams served as a clearinghouse for observation planning, allowing different groups to coordinate efforts and avoid duplication, while ensuring all critical measurements were attempted. Southern Hemisphere facilities, the European Southern Observatory in Chile, the South African Astronomical Observatory, and the Anglo-Australian Telescope took on increasing importance as the object's southern celestial position made northern observatories less effective. Scheduling challenges intensified as multiple groups competed for time on the limited number of large southern telescopes. Amateur astronomer contributions remained valuable through the fading process. While individual amateur telescopes couldn't match professional facility sensitivity, coordinated amateur networks achieved effective aperture increases through simultaneous observations that could be combined. Image stacking from multiple observers, when carefully calibrated and aligned, produced composite images with signal-to-noise ratios approaching those of larger single apertures. This collective approach extended the amateur community's ability to contribute scientifically useful data several months beyond when individual observers would lose the target in noise. The psychological pressure of a closing observational window affected decision-making about which measurements to prioritize. Every observation attempt represented a choice allocating telescope time to 3I. Atlas meant not observing something else. As the object faded and opportunities dwindled, this opportunity cost increased. Proposals had to argue not just that observations were scientifically interesting, but that they were more valuable than alternatives, and that the information couldn't be obtained once the object became too faint. This calculus favoured observations addressing the most significant anomalies measurements that might resolve key mysteries, like the straight jets the water deficit, or the nickel enhancement over incremental monitoring that added data points without qualitatively new information. Plans for final observations before the object faded beyond reach focused on obtaining the most constraining possible measurements. High-priority targets included resolved imaging at the highest achievable resolution to measure nucleus size directly if possible, deep spectroscopy searching for molecular species not yet detected but predicted by various compositional models, photometric monitoring through a complete rotation to measure the light curve with minimal noise, and astrometry precise enough to detect any remaining trajectory anomalies as the object moved beyond planetary perturbation range. Executing these observations required luck with weather, telescope availability, and the object's cooperation in not dimming faster than predicted. The final observation window represented more than just a scheduling challenge. It was a recognition that the opportunity to study this interstellar visitor was finite and rapidly approaching its end. Once 3I Atlas faded below detection limits, it would join the vast majority of cosmic phenomena that pass through observable range without being fully characterized, their mysteries preserved in partial datasets that future astronomers might re-examine but could never supplement with new observations. The urgency to extract maximum information before this deadline created a scientific race against the inexorable mathematics of distance and dimming light, the institutional response pattern. NASA's communication strategy surrounding 3I Atlas followed patterns established during previous high-profile astronomical events, emphasizing coordinated messaging and early narrative framing. The live-streamed presentation of the multi-mission image gallery served as the centerpiece of this strategy, bringing together observations from nearly 15 different spacecraft and telescopes into a single curated release. This coordination achieved several objectives. It demonstrated NASA's leadership in planetary science, showcased international collaboration, and, most importantly, established an official interpretation of what the data showed before alternative narratives could gain traction in public discourse. The presentation's script opened with definitive statements. 3I Atlas is a comet. Its composition, while unusual, falls within explainable ranges, and speculation about non-natural origins is unfounded. These assertions came before most viewers had the opportunity to examine the images themselves or understand the underlying data quality and limitations. The rhetorical strategy preempted questions by answering them in advance, a technique effective for shaping initial public perception, but problematic for scientific discourse, where questions should precede conclusions. The framing created an environment where questioning the comet classification or raising alternative hypotheses risked appearing contrarian or pursuing fringe theories. Behind this public presentation, internal communications revealed more nuanced and sometimes conflicting views. Email exchanges between mission scientists, preserved in Freedom of Information Act requests from science journalists, showed active debate about interpretation of specific anomalies. Some researchers expressed frustration that uncertainties evident in technical discussions were being smoothed over in public communications. Others defended the approach, arguing that presenting unsettled questions to general audiences invited misinterpretation and sensationalism. This tension between complete transparency and strategic messaging isn't unique to NASA or 3I Atlas. It represents a persistent challenge in science communication, where accuracy, completeness, and public comprehension often pull in different directions. The institutional response to the November straight jet anomaly illustrated these dynamics. Initial observations from Paranal Observatory circulated within the research community through informal channels, conference presentations, email lists, and preprint servers before any official agency statements. As recognition grew that the observations posed serious challenges to standard comet models, different institutions approached communication differently. The European Southern Observatory issued a carefully worded press release noting intriguing features requiring further analysis without speculating about implications. NASA initially declined to comment, citing ongoing data calibration, before releasing a statement weeks later that acknowledged the straight jets while emphasizing that multiple natural explanations were being investigated. This delayed response pattern, initial silence followed by general acknowledgement without specific technical details, frustrated researchers seeking clearer institutional positions on how to interpret the anomaly. Some viewed the caution as appropriate scientific conservatism, avoiding premature conclusions before thorough analysis. Others saw it as excessive risk aversion, prioritizing reputation management over advancing scientific understanding. The debate reflected different philosophical approaches to communicating uncertain or anomalous findings. Whether institutions should lead by offering interpretations and frameworks, or follow by synthesizing what emerges from broader scientific discussion. Resource allocation decisions provided another window into institutional priorities. During late 2025, as 3I Atlas observations competed for telescope time with regularly scheduled programs, different facilities made different choices about how to balance this target of opportunity against other commitments. Observatories with flexible scheduling accommodated more 3I Atlas observations, while facilities with rigid advanced planning provided less coverage. These decisions weren't purely scientific, they involved administrative judgments about the value of studying an anomalous but transient target versus maintaining commitments to longer-term survey programs and previously approved projects. The variation in how institutions handled these trade-offs revealed different organizational cultures and priorities. The handling of the NASA image embargo during the government shutdown became particularly contentious. While routine Mars reconnaissance images continued to flow from publicly accessible archives, specific requests for high-resolution 3I Atlas images from the Mars Reconnaissance Orbiter's HiRISE camera were delayed or denied. Official explanations cited technical factors, ongoing calibration, data quality concerns, standard review processes. However, the selective nature of the restrictions, allowing some mission data through while holding others, generated speculation about motives. Critics suggested that surprising or difficult to explain features in the unreleased images were driving the delay, while defenders maintained that the embargo reflected normal procedures applied uniformly, regardless of content. Internal reviews of how NASA handled 3I Atlas communications, conducted by the agency's Inspector General's office following complaints from researchers and journalists, revealed decision-making processes that prioritized consistency and control of messaging. Draft press releases underwent multiple revisions, with early versions containing more technical detail and acknowledgement of uncertainty being edited towards shorter, more definitive statements. Recommendations from communication specialists often overrode preferences from scientists for more nuanced language. The review concluded that while no policy violations occurred, improvements in balancing transparency with message clarity would benefit future communications about anomalous phenomena. International coordination added complexity to institutional responses. With observations coming from facilities in multiple countries and data analysis distributed across institutions worldwide, no single agency controlled the narrative. Different national space agencies and research organizations had different communication policies and relationships with media and public audiences. Attempting to coordinate messaging across this distributed network proved challenging, with information sometimes emerging from unexpected sources: a university press office, a conference presentation, a social media post by an involved researcher before official channels had agreed on framing. This distributed nature of modern astronomical research limited any institution's ability to tightly control how findings were presented and discussed. The episode provided case study material for future discussions of how scientific institutions should handle observations that challenge established understanding. The balance between appropriate caution and excessive conservatism, between accessible communication and complete technical disclosure, between coordinated messaging and individual researcher freedom to discuss findings, these tensions have no perfect resolution. Different stakeholders legitimately prioritize different values: public understanding, scientific accuracy, institutional reputation, research, community autonomy. How NASA and other agencies handled 3I, Atlas communications, satisfied some of these values while frustrating others, offering lessons about the inherent difficulties in science communication around genuinely puzzling phenomena, where honest acknowledgement of uncertainty might appear less authoritative than definitive statements, even when confidence isn't fully warranted. The plasma environment nobody's modelling. Plasma physics governs much of the observable universe, yet cometary science has traditionally treated plasma effects as secondary phenomena, important for understanding ion tails and solar wind interactions, but not fundamental to the object's behaviour. This perspective stems from solar system comet observations where neutral gas and dust dominate the near-nucleus environment, with ionization occurring primarily in the outer coma after molecules have travelled significant distances from the surface. For 3I, Atlas, MAVEN's detection of the enormous hydrogen envelope and the peculiar behaviour during the predicted coronal mass ejection encounter suggested that plasma processes might play a more central role than standard models assumed. The physics of plasma formation around comets begins with photoionization, solar ultraviolet photons, striking neutral atoms and molecules with sufficient energy to eject electrons, creating positively charged ions and free electrons. This process occurs continuously throughout the coma, with ionization rates depending on the ultraviolet flux, which varies with solar activity, and the neutral gas density and composition. Different molecules have different ionization potentials. The minimum photon energy required to strip an electron, meaning that some species become ionized more readily than others. Water, carbon monoxide, and carbon dioxide all ionize at slightly different rates, creating a mixed plasma with composition that doesn't necessarily match the neutral gas composition. Once ionization occurs, the newly created charged particles interact with magnetic fields carried by the solar wind. Unlike neutral molecules that travel ballistically away from the nucleus, following trajectories determined by their initial velocity and solar radiation pressure, ions become trapped on magnetic field lines and gyrate around them while drifting along the field direction. This fundamentally different behaviour means that the plasma and neutral gas components of the coma can separate spatially, creating regions where ions dominate and others where neutrals prevail. The boundary between these regions, called the ionopause, marks where magnetic pressure from the solar wind balances thermal pressure from the neutral gas. For 3I, Atlas, the large hydrogen cloud detected by MAVEN implied substantial plasma production, even given the low water abundance. If most of the hydrogen rapidly became ionized through photoionization and solar wind charge, exchange reactions where solar wind protons steal electrons from neutral hydrogen atoms, then the plasma density in the comet's environment could substantially exceed what the neutral component alone suggested. This ionized hydrogen, invisible to MAVEN's Lyman alpha detector that only observed neutral atoms, would interact with the solar wind's magnetic field and could potentially affect the behavior of dust particles if those particles acquired electric charges. Dust charging in plasma environments occurs through several mechanisms. Photoemission, ultraviolet photons, striking dust grain surfaces and ejecting electrons, typically gives grains positive charges. Simultaneously, free electrons and ions from the surrounding plasma strike grain surfaces, with electrons more mobile and faster than ions, tending to charge grains negatively. The equilibrium charge state depends on which process dominates, varying with grain size, composition, solar radiation intensity, and local plasma density. For submicron grains in the intense radiation environment near perihelion, positive charging through photoemission typically dominates. Larger grains might achieve different charge states depending on their specific properties. Charged dust particles experience forces from electric and magnetic fields that neutral particles don't feel. The Lorentz force, the combined effect of electric and magnetic fields on charged particles, can deflect dust trajectories, potentially confining particles along magnetic field lines or creating organized flow patterns. If the magnetic field configuration around 3I, Atlas, had particular structures, charged dust might follow paths aligned with those structures rather than simply radiating outward in all directions. This mechanism offered one potential explanation for the straitjets. If dust particles became highly charged, and if organized magnetic fields existed, the jets might represent dust flowing along field lines rather than tracing surface rotation. Testing this hypothesis required measuring or constraining the magnetic field environment around 3.1 Atlas. Unfortunately, no spacecraft passed close enough to directly measure fields in the comet's vicinity. Remote sensing of magnetic fields is extremely difficult. Fields don't emit light and can only be inferred through their effects on observable phenomena. In principle, polarization of scattered sunlight from dust can carry information about magnetic field alignment if dust grains align with field directions. Analysis of polarization measurements from ground-based observations showed no clear evidence of systematic grain alignment, though the measurements carried large uncertainties and couldn't definitively rule out modest field strengths below detection thresholds. Theoretical modelling of the magnetic field environment provided estimates based on solar wind conditions and the comet's gas production rate. The solar wind carries a magnetic field frozen into its plasma, typically a few nanotesla in strength at Earth's orbital distance. As this magnetized solar wind encounters the neutral gas cloud around a comet, the field drapes around the obstacle, creating a characteristic pattern with field lines wrapped around the coma. The strength and detailed structure of this draped field depend on the neutral gas production rate higher. Outgassing creates a more robust obstacle that stands off the solar wind at greater distance. For 3I, Atlas's estimated gas production models predicted draped fields of several to tens of nanotesla in the inner coma. Whether these field strengths suffice to organize dust into the observed jet structures required calculating the Lorentz force on charged grains and comparing it to other forces acting on the particles. For submicron grains with typical positive charges achieved through photoemission, the Lorentz force in a 10 nanotesla field proved insufficient to significantly deflect trajectories, radiation pressure, and gas drag forces dominated. However, if grains achieved much higher charges than typical, perhaps through secondary electron emission cascades or unusual grain properties enhancing photoemission, Lorentz forces could become competitive. This scenario required special pleading, assuming grain charges orders of magnitude above standard values without independent evidence that such high charging occurred. An alternative plasma-based mechanism invoked electric fields rather than magnetic fields as the organizing influence. Charge separation in the coma with photoionization, creating ions and electrons that then separate spatially due to their different masses and mobilities, can establish electric fields. If these fields achieved sufficient strength, they could accelerate charged dust particles, potentially organizing flow patterns. However, plasma physics places constraints on sustainable electric field strengths through debye shielding. The tendency for plasma to rearrange itself to neutralize electric fields on scales larger than the debye length, typically meters to kilometers in cometary plasma. Creating electric fields strong enough to organize jets over megameter scales required exceeding these natural screening effects, implying non-equilibrium conditions or unusually low plasma densities that reduced shielding effectiveness. Laboratory plasma experiments provided limited guidance for understanding 3I, Atlas's environment. Reproducing cometary plasma conditions, low densities, strong ultraviolet radiation, dust-grain interactions in terrestrial facilities proved challenging. Experiments studying dusty plasmas in vacuum chambers, originally developed for fusion research and semiconductor processing, showed that charged dust particles could self-organize into structured patterns under certain conditions, forming crystalline lattices or flowing streams. However, the conditions producing these laboratory phenomena differed substantially from cometary environments, and scaling the results to the megameter scale jets observed in 3I Atlas required extrapolations of uncertain validity. The plasma physics community's engagement with the 3I Atlas anomalies remained limited through late 2025. Cometary science and plasma physics, despite their obvious overlap, represented somewhat separate research communities with different journals, conferences, and funding sources. Plasma physicists studying solar-wind interactions, magnetospheric physics, and laboratory plasmas didn't routinely follow cometary observations in detail. Conversely, cometary scientists often had limited training in advanced plasma physics beyond basic ionization and solar wind deflection concepts. This disciplinary separation meant that sophisticated plasma physics tools and concepts weren't immediately brought to bear on understanding 3I Atlas, potentially leaving insights undiscovered. Some researchers began advocating for prioritizing plasma diagnostics in future interstellar object observations. Spectropolarimetry, measuring how the polarization of light varies with wavelength, could provide information about plasma density and magnetic fields through their effects on emission line shapes and polarization states. Radio observations at appropriate frequencies could probe free electron densities directly. If future interstellar visitors were detected with sufficient warning, spacecraft missions equipped with in-situ plasma instruments could be directed toward them, though the fast flyby speeds of hyperbolic trajectories would limit contact time and make such missions extremely challenging to execute. The lessons from 3I Atlas suggested that understanding these objects might require taking plasma environments as seriously as traditional composition and structural characterizations. What detection timing reveals? The discovery circumstances of 3I Atlas contained peculiarities that deserved scrutiny, independent of the object's subsequent anomalous behavior. First detection occurred on a specific date through a specific survey telescope, but the question of when the object could have been detected and why it wasn't found earlier carried implications for understanding both its properties and the selection effects governing interstellar visitor discoveries. Every astronomical discovery reflects not just what exists, but but what our search capabilities can find and when chance aligns with readiness. For 3I, Atlas, reconstructing its pre-discovery trajectory, revealed opportunities for earlier detection that were missed, raising questions about whether the object's properties, or pure chance, explain the timing. Automated sky surveys, like the Asteroid Terrestrial Impact Last Alert System, ATLAS, continuously monitor the sky, searching for moving objects. These surveys detect asteroids, comets, and other solar system bodies through their motion against the fixed stellar background. Images taken hours or nights apart show most stars in identical positions, while moving objects shift location, revealing themselves through this motion. The sensitivity of such surveys depends on object brightness and motion speed, with optimal detection occurring for objects bright enough to stand above noise in individual exposures and moving slowly enough that their trails don't blur excessively during exposure times. Backtracking 3I Atlas's orbit allowed calculation of where it should have appeared in the sky during months preceding discovery, and which survey telescopes had those sky regions in their observation footprints. The analysis revealed that the object passed through fields observed by Atlas and other surveys multiple times before the eventual discovery detection. Working backward through these earlier opportunities and calculating the expected brightness at those dates showed the object should have been detectable above the survey's magnitude limit in several instances weeks before the actual discovery. The question became why these earlier opportunities were missed when the object should have been visible. Several technical factors could explain missed detections. Sky surveys generate enormous data volumes, millions of images containing billions of detected sources. Automated pipelines filter these detections, searching for moving object candidates while rejecting artifacts. Cosmic ray hits on detectors, satellite trails, reflections from bright stars, and other spurious signals. The filtering algorithms use criteria like motion consistency, requiring detections in multiple images, showing coherent motion, brightness, stability, rejecting sources that vary too rapidly, and distinction from image defects. Legitimate moving objects can fail these filters if their properties happen to mimic artifact characteristics. Fast motion might be rejected as implausible. Brightness variations from a rotating nucleus might trigger rejection as unstable, or coincidental alignment with image defects might cause elimination as probable artifacts. 3I, Atlas's retrograde orbit, created motion patterns that survey software might flag as suspicious. Most solar system objects, asteroids in the main belt, near-Earth asteroids, even most comets move prograde in the same direction as Earth's orbital motion. Survey pipelines optimized for finding these common objects tune their motion filtering accordingly, prioritizing detection of prograde trajectories while sometimes being less sensitive to retrograde motion, which can appear unusual and therefore suspect. An interstellar visitor on a nearly perfect retrograde path through the ecliptic would exhibit motion patterns that, while physically legitimate, might score lower in pipeline ranking algorithms trained primarily on prograde object statistics. The timing of solar conjunction complicated early detection possibilities. For several weeks around October 21st, 3I, Atlas's position on the sky was very close to the Sun's position from Earth's perspective. Observing objects near the Sun is difficult because the bright sky during daytime prevents detection, and even twilight observations, shortly after sunset or before sunrise, face severe sky brightness that overwhelms faint sources. The object's trajectory geometry placed it within about 30 degrees of the Sun. The elongation angle during much of October, significantly reducing detection probability during that critical period around perihelion when it was intrinsically brightest. However, the object's brightness before and after conjunction should have made detection possible during windows when elongation exceeded 30 to 40 degrees and sky observations became feasible. The pre-conjunction window occurred in September and early October as the object approached perihelion, while still at reasonable elongation for evening observations. The post-conjunction window opened in late October and early November as the comet emerged from the sun's glare into the morning sky. The actual discovery fell in the post-conjunction window, but the September opportunities remain puzzling. The object should have been detectable then if observations were conducted and data properly analysed. Investigation into survey observing logs revealed partial answers. Some nights, when 3I, Atlas's field, should have been observed, were lost to weather clouds, high humidity, or equipment issues prevented data collection. Other nights, fields were observed, but images were rejected during quality control for seeing degradation, background brightness issues, or calibration problems. The survey's observing strategy prioritized certain sky regions, areas where potentially hazardous asteroids concentrate over others, and 3I, Atlas's location, didn't always fall in high-priority zones during the pre-discovery windows. The combination of these factors reduced but didn't eliminate pre-discovery opportunities. Data mining retrospective searches through archived survey images after the discovery attempted to recover pre-discovery detections. These searches used knowledge of the object's precise orbit derived from post-discovery tracking to predict exactly where it should have appeared in archived images, allowing focused searches in specific image regions at specific times, rather than relying on the original automated pipeline. Several pre-discovery detections were recovered this way, showing the object present in archived images that had been collected but where automated processing had missed the detection. These recoveries extended the observational arc, the time span between earliest and latest observations, improving orbital determination precision. The recovered pre-discovery detections revealed that the object had been captured but not recognized, supporting the interpretation that pipeline filtering, rather than observability, explained the initial missed opportunities. This finding carried both reassuring and concerning implications. Reassuring because it confirmed that survey hardware and observation planning were adequate to detect the object, but concerning because it showed that software processing steps were the failure point. If data existed but wasn't recognized, it suggested that other interstellar visitors might similarly be hiding in archived data, detected but not identified as noteworthy. The fraction of interstellar visitors we discover might be limited more by our ability to recognize them in existing data than by telescope capabilities to collect that data. The detection timing also revealed information about the object's brightness and activity evolution. By measuring brightness in the recovered pre-discovery images and comparing to post-discovery photometry, researchers reconstructed how the object's brightness changed as it approached and passed perihelion. This light curve provided constraints on activity onset and evolution, whether outgassing and dust production increased gradually or turned on suddenly at specific heliocentric distances. The data showed relatively gradual brightening consistent with steadily increasing activity as solar heating intensified, without sharp discontinuities suggesting sudden activation of major outgassing sources. Comparing 3I, Atlas's discovery circumstances, to those of previous interstellar visitors provided context. Oumuamua was discovered well after its perihelion passage, already outbound and fading, purely by chance when it happened to pass relatively close to Earth, making it briefly bright enough to detect despite producing no cometary activity. Comet Borisov was discovered while inbound, months before perihelion, providing much more observation, time, and data. The discovery timing strongly affected what could be learned about each object. Borisov's early detection enabled comprehensive characterization, while Oumuamua's late discovery left major mysteries unresolved. 3I, Atlas's discovery, fell intermediate, post-perihelion, but not long after, allowing some observations during active phases, while missing some of the approach data that earlier detection would have provided. This pattern raised questions about the true rate of interstellar visitors through the solar system. Current estimates, based on the small number of confirmed detections and models of interstellar object populations, suggest 1 or 2 detectable visitors per year pass through the inner solar system. However, detectable depends critically on brightness, trajectory, geometry, and the specific capabilities and observing patterns of sky surveys. Objects on trajectories that keep them far from Earth pass through solar conjunction during their brightest phases, or move in patterns that automated pipelines filter, as probable artifacts might go undetected even if they reach brightnesses that should nominally allow discovery. The true rate of interstellar visitors could substantially exceed current estimates if detection efficiency is lower than assumed. Future survey systems promised improved sensitivity and better algorithms that might increase interstellar visitor detection rates. The Vera Rubin Observatory's legacy survey of space and time, scheduled to begin operations in the coming years, will scan the sky with unprecedented depth and cadence, detecting fainter and faster-moving objects than current surveys reach. Machine learning algorithms trained specifically to recognize unusual motion patterns, including retrograde orbits and hyperbolic trajectories, might reduce false rejections of legitimate interstellar visitors. However, even perfect detection systems face fundamental limitations, from geometry objects passing through solar conjunction during their brightest phases will remain difficult to observe regardless of how advanced our telescopes become. Some fraction of interstellar visitors will inevitably escape detection simply through unfortunate timing of their passages through the regions of sky we cannot efficiently observe. The trajectory that defies prediction. The numbers refuse to align. When 3I, Atlas, passed within 19 million miles of Mars, gravitational physics demanded a measurable deflection in its trajectory, several arc-seconds of deviation as the planet's mass tugged at the passing visitor. JPL's orbital determination team ran the calculations repeatedly, adjusting for solar radiation pressure, outgassing forces, and potential mass distribution asymmetries. Each iteration produced the same uncomfortable result. The deflection was minimal, bordering on negligible. For an object estimated between 1 and 5 kilometers across, this Mars encounter should have left an unmistakable gravitational signature. It didn't. Standard orbital mechanics operates on principles refined through centuries of observations. The equations governing motion through space account for gravitational attractions from the Sun, planets, and major asteroids, plus non-gravitational perturbations from radiation and gas jets. Software like JPL's Horizons system successfully predicts trajectories for thousands of objects with high precision. When these proven tools processed 3I, Atlas tracking data, something fundamental broke down. The residuals differences between predicted and observed positions showed systematic trends rather than random scatter, suggesting the models were missing something important about how this object moves through space. The Southwest Research Institute's team attempted to model the non-gravitational accelerations that might explain the discrepancies. They built detailed thermal models calculating how sunlight would heat different surface regions and drive gas production, predicting acceleration vectors that should match observed trajectory deviations. the predictions failed comprehensively. The direction of observed accelerations didn't align with where thermal models placed the most active outgassing regions, and the magnitude seemed too large for the estimated gas production rates. Spectroscopic measurements showed relatively modest outgassing compared to typical comets at similar solar distances. Yet the trajectory displayed accelerations consistent with much more vigorous activity. By mid-2025, 3 independent research groups had published orbital solutions using different modelling approaches and datasets. All 3 reached the same frustrating conclusion. The object's motion required forces beyond standard gravitational and radiation effects, and these additional forces showed structure and persistence that didn't match random outgassing. The Minor Planet Center appended a note to their catalogue entry acknowledging the trajectory uncertainties and recommending caution with long-term predictions, a rare admission that current models couldn't reliably forecast where. This visitor would be years into the future. For the planetary defense community, these modeling struggles carried serious implications. Their mission involves identifying potentially hazardous objects, calculating impact probabilities, and developing mitigation strategies, all depending on accurately predicting where objects will be decades ahead. If interstellar visitors move in ways current models can't capture, then the entire framework for assessing impact risk needs revision. A fast-moving interstellar object on an Earth-crossing trajectory might not provide adequate warning time if trajectory predictions carry large uncertainties. The rotation problem deepened the mystery. Photometric monitoring produced an unusually precise measurement. 16.16 hours, confirmed independently by multiple observatories. Light curves showed the characteristic double-peaked structure expected from an elongated body tumbling through space. With this rotation period fixed, physics left no ambiguity about expected outcomes. Any jet ejected from a specific surface location should trace a spiral path through space, with the curve determined by outflow velocity and the rotation carrying its source around the nucleus. Over roughly 29 days required for particles to travel 1 million kilometers at typical speeds, the nucleus would complete approximately 43 full rotations. The geometry of rotating jet sources has been studied extensively in solar system comets. Material released from a spinning nucleus carries angular momentum, creating spiral patterns where jets curve opposite to the rotation direction. For 3I Atlas's measured parameters, calculations predicted jets should show clear curvature, bending by tens of degrees over distances of hundreds of thousands of kilometers. The November images from multiple observatories showed jets remaining straight across distances exceeding 1 million kilometers, a violation of predictions too large to dismiss as measurement uncertainty. Several mechanisms were proposed to reconcile straight jets with confirmed rotation. Polar jets, active regions at rotation poles where velocity is zero, would eject material radially without rotational deflection. However, this required all observed jets to originate from polar regions, inconsistent with images showing jets at various angles as the object tumbled. Moreover, polar regions receive less solar heating than equatorial areas, making them unlikely hosts for vigorous outgassing. Alternative explanations involving rapid precession or extremely fast outflow velocities faced their own insurmountable problems when detailed modelling revealed they couldn't eliminate the expected spiral structure. Laboratory experiments at the Southwest Research Institute attempted to reproduce the straight jet phenomenon. Vacuum chamber tests spun ice and dust mixtures while simulating solar heating, allowing jets to form as ice sublimated. The jets invariably showed predicted spiral structure. Varying rotation rate, outflow velocity, and surface properties changed the spiral's appearance, but never eliminated it. The experiments confirmed that standard physics couldn't produce straight jets from rotating sources under conditions relevant to cometary outgassing. Computer simulations provided another testbed, tracing paths of millions of individual particles ejected from rotating nuclei while accounting for gravity, radiation pressure, and gas drag. The simulations produced detailed visualizations under various assumptions about rotation states and nucleus shapes. In no configuration did they reproduce straight, undeflected jets extending to million-kilometer scales from a body spinning every 16 hours. The physics was unambiguous. Rotation should produce curvature, and that predicted curvature was absent from observations. The trajectory now carries 3I, Atlas, toward regions where tracking becomes progressively more difficult. Its southward path shifts observation opportunities to southern hemisphere facilities as it fades from northern telescopes. Distance creates inexorable dimming brightness, falls following inverse square laws with both solar distance and Earth distance, making every passing month significantly degrade observing conditions. Spectroscopic observations, requiring the highest brightness levels, became impossible first. High-resolution spectroscopy, necessary for detecting weak emission lines, lost viability as brightness dropped below 18th magnitude. Even basic imaging faces limits, with resolved coma structure requiring sufficient brightness to reveal extended features against sky background. The observational window closing means the trajectory anomalies may never be fully resolved. Once 3I, Atlas, fades below detection limits, it will carry its mysteries back into interstellar space, leaving partial datasets that future astronomers might re-examine but can never supplement with new observations. The Mars encounter that should have provided a clean gravitational test instead added another puzzle to a growing list. An interstellar visitor is moving through our solar system following rules we don't fully understand, heading outward on a path we can't reliably predict, fading from view before we've answered the most fundamental questions about what forces govern its motion through space.